Welcome, everybody. It's really good to see you all. It's been an amazing 2 weeks. I want to make sure I thank all the participants that were helping the auditory group. I'll try to thank you all again at the end. But it's really been amazing to see all the efforts and all the good stuff and all the collaboration. It's been really wonderful. And I want to summarize what we've been doing for the last 2 weeks in these four broad areas. A bunch of stuff on AI and all the good stuff that's coming because of AI. A big part of our workshop this year is on motor control. So how the auditory system and motor work together. And so we have some results there. We've done a bunch of work that we've classified as embeddings, machine learning. So more traditional things like building embeddings, and I doing machine learning on top of that. And then we have a couple of other papers that sort of fall in the other category. And all these details, which you can't see, will be filled in over the next 39 minutes and 8 seconds. So with that, going.
Okay. So what we had a data set of, thanks to RJ, was there were a whole bunch of people who were in fMRI projects at fMRI systems listening to podcasts. And he, in previous work, had found that there are, if you take the words that the person was listening to and tokenize it and into these higher dimensional embedding space, that you can find these correlations for certain areas of the brain that are activated more strongly with the tokens than others. So this suggested that there are actually there was the way that information is encoded is not dissimilar to the spatial. Like you can get some spatial information from the brain, like related to the.
We haven't had those because we have to for the target for that.
Related to how the tokens are embedded. So, but that's not really interpretable. So what we've done now is we've extended this into trying to cluster those topics, those embeddings into specific topics. So we can actually probe, like maybe there's certain parts of the brain that are more correlated with things like words associated with the beach or oceans or something. Maybe this person has some strongly held beliefs about that. Or maybe there's religion or God or politics or something like that. So, do you want to sort of? Actually, I'll run this up then. Okay, so we took all of the topics from these podcasts that people listen to, so just using some clustering, used some regression, and then visualize the flat map for how these topics are sort of correlated. This is what we were just doing this yesterday. So there's actually certain parts of the brain. So these red areas, the whiter areas, they were more they more accurately distinguished between different types of topics. So they were either turned on or off by specific things. So you can actually submit that. We're actually going to start probing which areas were like more selective between the topics that they actually sort of heard at the time versus others. It is an interesting kind of part thing to that we found. There was do you have the parts of the brain that RJ was talking about?
Yeah. So the three of us don't really know anything about brains, but the other person on the project who does, they were saying that there's regions that are place sensitive. For example, the retrosplenial cortex, the parahippocampal place area, and those are selected for fewer topics than regions in the temporal lobe. And this is also like a nice sanity check here, where you can see that there's a lot of activity in like the auditory cortex, which makes sense because people go switch podcasts.
So the next bit of work that we're going to be doing is actually teasing those apart, and maybe we can find certain areas that are more interested in certain things than others.
Good. That's
Yeah.
There'll be lots of things to applaud at the end. I think we're all done. Go ahead.
Okay, so this next project was me, Jackie Rupesh, and Nima, And we were building on top of some existing work that had come out of Nima's lab at Columbia with the Listen, Chat, Explain audio foundation model, which takes in a mixture of sounds. They've taken 4 sounds, like 2 speech sounds and then 2 other sounds like animal call. And then you can edit those sounds by interacting through an LLM and saying, like, please remove the sound of the person who has a voice and amplify the pitch of song. And so we were interested in this idea of a sound object, like when there's multiple sounds in this recording, how does the model actually distinguish that like this part is the pigeon, and how does it do this editing? And so this was like a very small dive into just examining the model. So we had like 2 tasks where we wanted to just like visually examine how the model is distinguishing between those sounds, and then also examine a little bit of the inner workings of the model by visualizing some of the high dimensional like work that's going into the mask that takes in that prompt from the LLM. And so first we had our own mixture of sounds that we came up with, and it was a woman, a man, a duck, and a gibbon, and I don't actually know what this 4th one was, like what animal. But so what we did is we just asked the model to delete the sound of the woman, and we looked at the FFTs for the 4 different sound sources and looked at the FFT of like the entire mixture at the beginning and when the woman was removed, to see if we could see like distinct frequencies that corresponded with the woman that were removed. And we couldn't really, there wasn't a big difference, and actually the duck is actually where we see the most difference.
Okay, yeah, so from what we found was basically how the model really, so it's a bit lag, how the model mostly separates information is via time points, basically, where if you have this slide, if you have certain time points where the target is present versus absent, that is what the model uses to separate out. So here on the right, we have time points per point on the T-SNP slide. And dark blue means the target you want to extract here, the woman speaking, was present. Light blue means it was less present, and these are all the intermediaries. So as you can see here, the points in blue are the time points you want to extract here, and the points in blue are the points that you want to remove for this task here. And for the whole point all the way through, you can see that the model really focuses on trying to separate, trying to cluster. Yeah, try to cluster. And with the semantic input from the LLM, the machine learning uses that to form semantic clusters. As you can see, you can form lots of clusters according to the semantic meaning behind the sound, but not much separation according to the time point. Whereas when given auditory information, the machine then uses that to separate according to the time point auditory presence.
So this project is a sensory motor decoding from the violin playing. Rupesh, Song, and Shirab is involved. So speaking and playing music involve both motor and auditory processing. So in this project, we want to understand can we or how auditory and motor process be entangled in the EEG signals. So the main goal is disentangle motor activity and auditory activity. So for that, we collect the violin playing data, which is playing here, and with the EEG on and the sound and the video. So from the video, we collect, we extract the pulse here. So the main goal is from the EEG, can we disentangle of the pose and the motor activity and the sound as well. So for that, we collect 3 different cases. First, playing the violin with the sound. Second, playing the violin without the sound, which is just motor activity. And we just listen what we just played. So as a result,
so we collected large of at least few participants while playing the violin and while they are mimicking playing the violin. And then we use the EEG data to predict the motor activities. So these are like preliminary results that we show here. So we use just the motor variables, which are basically the pose and the velocity. So as you can see that in the first panel is the ground truth of the motor, which is pose and velocity. So this is what we reconstructed from the EEG channels. So the bottom panel is basically one of the channels that we plot. So the red curve is what is reconstructed and the blue curve is the ground truth. As you can see that it's closely matches with it. So we were able to reconstruct the motor variables just from the EEG. This is while playing the violin and this is while they are mimicking playing the violin. So then we ask another question. How will the model actually model from case 1 predicts the motor variables from the case 2 and vice versa? That means you have violin playing and then can we use that model, the model trained on violin playing to predict the activity on mimicking violin playing. So as you can see that here also like, we get fairly good good comparison with the ground truth in both the cases. So there is a lot of processing that need to be done, but we are excited about this data. Thank you.
Hello.
Okay, so this is the mountain bike project. So I've been working with Nahale, Lucas, and Toby down there. So basically what we wanted to do was try to see if we could decode from EEG, continuous action planning, and error feedback. So basically we had participants playing a mountain bike game. So you see here they have to try to stay on path. And we recorded EEG, pupillometry, eye gaze, together with the steering and the steering error. We then used a linear decoder to try to predict the continuous steering and the steering error, but with a good anticipation so that we could use this for a BCI potentially. So, so here in this video, this is my no result. so here what you see is basically the EEG decoder trying to play the game. So basically the decoder is predicting the steering and giving this as input to the mountain bike game. So you can see it's very noisy. And there is a lot of work to do, but we have a bunch of ideas how to isolate motor-related activity from unrelated activity in the brain and noise. And I guess this can really bring some improvement.
To the next slide.
space bar, yeah.
So as Georgia mentioned, we're also recording eye tracking and pupillometry data. You can see an example recording during one session here. So the bottom one is IR eye cameras and the top one is gaze data, which is following the trail on the game. Using this data, we can compute an average pupil size over the trials shown here in blue. And we also have the maximum steering error during the game here in red. You can see that they're both decreasing, which is a good sign, but this is the data for only one subject, so it's pretty soon to do any conclusions. But the hope is that we can use the pupil size as an extra marker to predict the error and further develop the decoder that Georgia talked about.
Why is it good that pupil size is decreasing?
Sorry?
Why is
Also, it's kind of correlated with the maximum steering error. So the maximum steering error is decreasing, the pupil size is also decreasing. So the hope is that they are correlated.
All right. Lucas?
this project is about haptic rhythm learning. Rupesh, Song, and Cornelius are involved. So learning complex rhythm is an easy task for the human, most of the human, and the crucial for the communication skills. So the question is, what are the neural correlates of the rhythm patterns of the rhythm perception in our brain and how it modulates during the learning? So to understand those activities, we designed this music learning, haptic music rhythm learning program that participants are asked to tap while the notes are rising, and then we record the tapping and the EEG of the before and after training, and then the song, so we can compute the error they made it, and we can see how the correlation between the EEG signal and how the tapping errors and things like that. So we collect a total 8 participants in the 10 session of each participants, and before the training and after that, we asked them to train over 5 days or the 7 days and almost 10 minutes per day. Thanks for the participants here. So then we collect pretty large data, and we can see some great results here.
So as Sung mentioned that we have collected like 10 session data. So in one case, like, participants were seeing the sheet music and listening to it and tapping. And in one case, like they are not seeing the sheet music. In the other case, like they are like listening. We have like a lot of controls which spans across like 10 sessions. So 10 sessions, as you also see, like I have like running around people just to record the EEG and training for this one. So what we show today is the behavior data. So each panel is that this is like while they're tapping during the Austrian anthem. So x-axis is basically before learning and after learning, and the y-axis is like how good and bad they are doing. So out of all the participants except 2, most of them moderately actually increase their rhythmic following during this thing. As I said, like we have like EEG of 8 subjects, which is like much more complex data, and then we were planning to analyze this data. Thank you.
Basically, you're saying that most of the subjects got better at tapping.
And that too only for 5 days or 6 days. I mean, for the longer time, definitely there will be.
Some got worse.
Yes.
Yeah, some got worse.
Who are they?
All right, so now we want to move to the embedding and ML stuff.
Yeah. So in this project, we are aiming to combine an ECOG and fMRI dataset for studying natural sound perception. And this project was done by Tia, me, Georgia, Damon, and Sam. So let's listen quickly to the sounds.
What's the sound sharing?
It's like a stream of very diverse sounds, like music, speech, nature, sounds. And so if we listen to these sounds, we can ask what aspects of the sound does the brain care about? Like, does it also make the distinction between music and speech and processing, for instance? And then also, when and where does it activate for this aspect? Now, the thing is that ECOG has a good temporal resolution of about 40 milliseconds, but it has very limited coverage. And then fMRI has large coverage and a good spatial resolution of about 2 millimeters, but it has no time information for our stimuli. And so now the idea is that if we have ECOG and fMRI responses for the exact same set of sounds, we can hyper-resolve ECOG in space and fMRI in time. So we started by reasoning that the average ECOG activity in the same brain area should be the same as the voxel activity in that area. And so we verified that by predicting the fMRI activity only as a weighted combination of the ECOG activity. And we found that we can reach a really high accuracy for those predictions in these areas. And there, it has to be noted that we are predicting for completely different subjects, different people, and also for completely different data. Yeah, data, kind of data.
Having verified this correlation between ECOG and fMRI, now we can combine the fantastic temporal resolution of ECOG and fantastic fantastic coverage and spatial resolution of fMRI to study how what aspect of sound the brain is processing. Okay, so we use non-negative matrix factorization. This is an unsupervised data composition technique. We did a joint factorization to make sure that we found components in ECOG and fMRI that share the same spatial and temporal pattern to sounds. The components here mean a weighted sum of voxels in fMRI or a weighted sum of electrodes in ECOG. What's amazing is that the model is agnostic to sound categories, but we still see this component that activate most for speech sounds. And this bottom one activate most for music. And what's even more amazing is that we can now reconstruct the brain response to these components with high temporal resolution, 40 milliseconds per frame, and great spatial resolution and coverage, as you can see from the video. We have some sound waves. That's all.
Yep.
Check, is the sound being shared? on
Yes.
Zoom? Okay, good.
But we have an echo if we turn it up too loud, and we said it worked before, but then we mucked with the settings and.
We want to make sure it's on the recording.
Yeah.
So UJ, Mara, Mate, and I, we've been working on studying language proficiency using EEG. So as you know, people may have different levels of English proficiency, and the question that we want to answer in this project is whether we can find neural markers in the EEG data that corresponds to these differences. The data set that we're using includes subjects with very little or no English understanding, and we also have non-native English speakers, which with proficiency varying between basic and proficient. There's a back here, sorry. And we also have native English speakers. So EEG data is recorded from these subjects while they're listening to sentences from a children's storybook. And they're also going through some behavioral tasks to make sure that they're attending to the stimuli. The first thing that we want to do is to pull out shared components from the EEG data to obtain what we call a denoised supersubject for each proficiency group, which is basically a representative of all the subjects in that proficiency group. And if we do a correlation analysis between the different supersubjects, we find that the subjects that have a closer proficiency level also have more similar brain responses, for example, here. So now that we have these different supersubjects, we can classify an unseen test subject into one of the proficiency groups by comparing its correlation with the different supersubjects. You can see our two-class classification accuracy for the non-native subjects here on the plot. And for example, we have like a 70% accuracy for classifying between basic and intermediate level subjects.
Yeah, so in addition to the MCCA analysis just mentioned, we also have done pairwise CCA analysis for every pair of subjects and every sentences. And among the several discoveries that we have made, the most significant one is that we found out the more proficient, the more various across subjects in the EEG data. So on the left, you can see here, if we have two subjects from the same group, let's say from group A, which is the least proficient one, then they actually have their EEG data to be more correlated than if you say you're native speakers. And then we verified the hypothesis through the analysis on the right, that we do a correlation between the EEG and the audio envelope and see that the non-English speakers has higher correlation for their EEG data against the audio envelope. So we concluded that mostly acoustic features drive the brain responses for less proficient subjects, which explain the higher intragroup correlation for low proficiency subjects.
Yeah, and then I also attacked the same task, but using deep learning models. And actually, I tried to use two neuromorphic inspired solutions for these tasks. So to basically classify the random EEG samples from the different participants to be able to tell like their proficiency. And the first task that you have to do is to embed the continuous time varying length EEG signals into a vector space. So to do that, I use the state space models, which are kind of like membrane potentials. So they're neuromorphic in that sense. And then another task that was very difficult was to generalize the findings to unseen participants. And to do that, I implemented sort of modern Hopfield network, an associative memory, like the hippocampus in a way, to use examples from the unknown participants as a sort of bottleneck to form linear combinations of them in order to predict the classes of the training samples. So in a way, the idea is to force the network to implicitly learn the labels of the unseen participants as a byproduct of having to do the classification. And the results have been that, so using just SSM models for the embedding, it works really well for the situations where we train on all of the participants. So it can classify any kind of proficiency with net 90% accuracy. And using a small model of only 155 parameters with only one channel, you can classify between basic and advanced speakers. And also, but the problem arises when you have to classify new subjects and the accuracy falls to random. But if you use the associative memory with as a kind of bottleneck there, it actually improves beyond the random. So it improves generalization using an associative memory. So it's a double neuromorphic solution for understanding brain data.
Cool, thanks.
So next is a quick experiment that's done by me and Molly. So I guess the main driver behind this is that it doesn't matter if you're using a machine learning method or a deep model. So for speech enhancement, what you're trying to do is you're trying to project the data point onto some space such that we hope that the speech data and the non-speech data can have distributions that are like separate from each other. So for here, we're trying to leverage the power of the pre-trained speech model and see if it can give us such embeddings. So our method includes that we're trying to analyze the higher dimension embeddings, and then we are using a pre-trained weight-to-vec embeddings to see if we can separate speech and non-speech. And here we're using data from English speech, non-English speech, and non-speech. So the result we got here is if we do a dimension reduction on the data itself, and then we do a PCA, we can actually see that the data from each of them form clusters for each of the classes. And with the centers of the clusters, we can actually just do a novel frame-to-frame classification. And for this sound clip here, yeah. So okay, okay. So you can see that in between the music here, there's a concept you can actually classify them as like non-speech. So the observations we have is that the binary classification for this works, but then it overshoots for speech. And then these are the caveats. So we have the silences to be misclassified as English speech, and we think it's because from the training data, there are silences in it. So they're all still like in the embedding space. And then for also, this is the most important part. So like for vocalizations, doesn't matter, it's like foreign languages, accented English, or even dog barking, they are misclassified as reverse English. So I guess the main takeaway here is, so the main takeaway is that if you have a dog barking, and then if you reverse it, you will hear this.
You have to read it.
Oh.
Okay, let's go. Let's move on. Sorry. It's going.
It's going.
Woof. Ooh, woof. Me love meat.
Okay, next project. We're gonna go fast. Because we're behind. But the idea was to use a music transformer for understanding natural music listening. So the the fact of the matter of the fact, whatever, is that when people listen to music, they are engaged in an active process in which they continuously predict musical events based on the structure, on the local context of the music, and on the long-term learning that they have from life exposure to their musical culture. So far, the community has used a simple Markov chain with n order that can be used to model musical expectations, so how people actually predict the next musical events. So those are simple, easy to interpret linear models. Very recently, because of the development of music transformer for music generation, some attempts have been made to use those to predict EEG data or just to gain understanding about musical representation in the brain. And so far, what we have found is that the output of music transformer in terms of, for instance, surprisal, only very marginally contribute to explain neural data. So here, what we start to do in this project is to dive more in deep into these music transformers and try to pick some other information from it that could be useful for understanding how the brain processes music and complex structure from music.
Well, as a prior results, we tested out the Chinese music and the European song to the music transformer, and we extract the embedding of the encoder of the music transformer, and we looked at actually music transformer can separate the Chinese music of the embedding and the European song is the embedding. So as you can see here, the blue dot is the Chinese music and the red dot is the Bach music. So the music transformer can actually separate the cultural background difference. So in the future works, we will see more diverse the music cultural songs, and we also get the surprise from the music transformer and how we relate it to the biomarker of the data set we have. Thank you.
Alvin, are you there?
Yep, I'm here. Hey, Malcolm, could you man the slides for me? Thank you. So yeah, this project, the goal was to basically see if you were to eavesdrop and a conversation, would it actually help to be looking at the speaker while you're eavesdropping, or could you be looking anywhere? And that would still be equally effective in terms of how much auditory attention you can pay in a particular direction. Could you go to the next slide, Malcolm? And the paradigm that we came up with was, let's say you had two speakers playing. I have a little sample of the audio where you would just hear maybe one person talking a little to the left and simultaneously another person talking a little to the right. And then we have two conditions in which one, you actually look at in the same direction as the talking speaker. And there's no like actual lips moving or a moving face. We wanted to not include that. It's just a matter of if you look in the direction of the speech or not, can we get like better correlation between EEG that we would measure compared to like some feature of the audio, let's say the speech's envelope. And could you go to the next slide, Martin?
Working on it. Thanks.
And this is just very raw data. I should preface that. So I collected data on one subject, that is myself, with like 12 minutes of each condition where I'm actually looking in the direction of the audio source or looking elsewhere. And then I just try to fit a linear filter, a TRF, between the EEG and the speech envelope. And I'm not really noticing much of a difference. So I think this will need some more processing. But actually, it was a lot of fun to coordinate like a project that was planned in Telluride, but the data was collected in San Diego. So overall, really enjoyed this hybrid experience. Thank you.
Thank you.
So the neural data visualization project is a collaboration between Georgia, and myself. So as you know, the EEG is of paramount importance for the neuroscience. However, the current tools, they make it hard to reason about the relation of the electrodes when they're recorded. Above all, they are quite tedious and kind of looking boring. So we are trying to fix that by with some artistic kind of input, trying to fix that. And what we do is we visualize the electrodes as they come, as the signals come from the electrodes, we visualize them in this on a 3D head, exactly in the same positions where the electrodes are on the headset, right? So we can uncover the brain. You can on the top you can see the actual the electrodes, the voltage, and here we show them on the brain. We can show them both on the skull and on the brain inside. The colors, they show the voltage. The red one is kind of high, the blue is low, and then we have different, like we can place these small needle-like probes where we can show additional information. For instance, here it's an alpha, beta, and gamma waves. It's like time series stuff like that. So to summarize, we have an intuitive visualization of the electrodes where they are actually in the real world. We place them in the virtual world. We have alpha, beta, and gamma extraction, and we have as well real-time FFT. We do that on GPU in real time. Yeah, it's a frequency analysis for every probe. You can see the frequency there. So the future work, our future goals are we want to open source it. The main reason is that researchers, you people could write a functions like a processing functions. We had some ideas like that we could correlate the electrodes and show them with lines which are correlating at every time step or a particular time. But I guess you will come with other interesting applications. We want to do a neural feedback loop. Basically, the person will be looking at the procedural art, and depending on their EEG, the art will be changing, the music will be changing, and then we could see the EEG again. How basically a loop, how does it affect? For the music, we would like to integrate it with Max Muse. And yeah, the goal is well to apply for one of the main graphics conferences next year to show it hopefully on stage as a cross-media application. Yeah, that's it.
Next slide. I think we've got this one. Next one. So it's been an amazing 2 weeks. I want to thank the participants again. It's all been really amazing. It's really nice to see everybody working together. I also want to note that this year was unusual. We had one remote participant who did really well. That's pretty impressive to see. It's really hard to keep up with this community when you're from far away. So Abu was a great example. This year we also had 2 people from town who participated. Daman, who's a recent RPI graduate, and Lucas is a high school student. So this is a really good sign for Telluride because now we have local talent we can grab onto. So I think the Neuromorphs can hopefully take, well, and Pinheads and everybody else can take some credit for bringing more technology to Telluride, and we have some homegrown talent, which is really great to see. So thank you, everybody.
We are going to
All right, so yeah, welcome from the Nick team as well. Was a very busy 3 weeks. There is a lot of topics on here. The slides have grown overnight, so we'll try to stick in the 40-minute time frame. To all of the presenters here also, then let's try to keep it short. So we have a couple of different projects. Most of these are really related to building new hardware. Some of them are related to running stuff on existing hardware. And I've put here the different technologies that we're using, and we will be going through the different projects one by one, and the participants will present each of these. And this is a little bit of context here. So hardware design is a very long, complicated process. And so for the hardware projects here, we've mostly been dealing with these first couple of steps here. So what you'll see is the initial steps in a lot of different projects. There's a lot more that needs to be done, and this is future work. So what we hope to have achieved here is to have started these projects, but most of the work is going to happen in the aftermath of this workshop. So keep that in mind. And I think we'll just start with the first project directly. So Ziha, do you want to, or who wants to present here?
So we're the voiceover group. So a little bit of background on the algorithm that we're working on. So we're working on the quadratic unconstrained binary optimization problem. So it's a class of combinatorial optimization problem. So the problem with this kind of problem is that the computation costs grow exponentially with the problem size. So in order to do that efficiently, we have this quadratic form that basically describes the cost or energy of the physical of the system. And the goal is to make the energy, minimize the energy so that we achieve the ground state of the system and well have the optimal configuration of the of the problem. So because the state in this case is binary, so one naive algorithm would be rejection sampling. So we first randomly select one of the node in the graph and flip the coin. So and if the flip is gonna help minimizing the total energy, we're gonna accept the flip. If the flip is not gonna help with the total energy, we just reject the flip. So but the problem with this kind of approach is also quite obvious, because if we're at a local minimum, there's no way we can go. So so as you can see here, the round flips, it's actually quite important to get to the local solution. So that's where we introduce some kind of noise, so that with some probability we accept the round flips. So how do we map that to a neuromorphic architecture? So we have so this criteria is the augmented one with the probability. So the mu n is the noise generated from external noise, and then delta H basically records the energy change of the network. So that's kind of familiar to the neuromorphic community, because it kind of maps to a very simple neuron model. So the member potential is actually the delta H here, and mu n is a stochastic firing threshold. So whenever the member potential cross this certain threshold, the neuron will will flip itself, and the spikes in this case is basically trying to for the spiking neuron, it's trying to inform the neighboring neuron that basically my state has been flipped. So this reservoir is basically a software simulation of the algorithm. So these are the neuron index, and it's a time loop with a 500 iteration time window. So now I'll go into the architecture a little bit, like the circuit that we designed for this kind of algorithm. So a quick overview of the architecture. So the pink blocks here are the neurons, and the neurons will generate a spike and send to the green network, and the network will do the selection and broadcast it back to all the neurons. So I will dive a little bit more into how the architecture of the neuron itself looks like. So inside the neuron, we have the member potential block, and this mu in is externally generated noise. So it's a plug and play piece of hardware. We can generate different distribution. We can generate noise from different distributions, and the distribution and the schedule of the noise is actually very important for the algorithm to perform well. And then the member potential and the threshold will be fed into a comparator, and the comparator will determine if the neuron will send a spike or not. And then the neuron will try to send the spike to the network. And for the receiving end of the neuron will also receive spikes from the network. Because it's a broadcast, the receiving neuron has to make the decision of whether I will take their spike or not. So this piece of logic is a lookup table that basically shows it's a local decision whether or not I will take the incoming spike or not. So if the neuron is to determine I will take the spike, they will use the information to update the member potential, and again this happens in a loop. So what we made a little bit of twist here is that we introduced a second clock, which is tied to the spiking activity of the neuron. So basically, if the second clock has a higher clock frequency, for example, it will introduce a race condition for this register that stores the spiking activity. So basically, even if the neuron decides I'm gonna spike, there's still a chance because of the metastable stage, the spiking activity will be inhibited. And we also try to put design the whole circuit and put it through synthesis and layout. But do you wanna
So we did the physical design of the whole chip. Now this is the physical design of a single neuron block. So a single neuron block had around 7.5K instance count, and it had a total area of 0.04 millimeters square. And so we did a hierarchical design where we first synthesized and we did the sign off of a single neuron block. And in the floor plan, we had 1,000 blocks that were arranged together. And this is the layout of the whole chip. So the whole chip had a dimension of 9 millimeter cross 9 millimeter because it had to accommodate 1,000 neuron blocks. And we ran the whole flow at a clock frequency of 200 megahertz. But since the chip size was quite large because it was 9 millimeter cross 9 millimeter, we had a slack of around 750 pico to 1 nanosecond. So therefore, what we are planning to do is we are planning to reduce the number of neurons in the block to 512. So when we go for a reduced count, then okay. So when we go for this was the initial design where we had 1024 neurons in the block. So in which every neuron consumed around 0.04 millimeters square. But when we went to a smaller architecture which consisted of 512 neurons, then the area of a single neuron block reduced by half. So therefore the area of the whole chip will reduce by 4 times. So that is the whole plan. So the plan is now to tape out the chip in 65 nanometer with a dimension of 2 millimeter cross 2 millimeter with 512 neurons. That's it. Thank you.
Or you can also come back.
Okay, yeah.
Dad, do you want to say anything about this or Shantanu? Jason, you want to talk about the neuro transition?
Thank you, everyone. So the chip presented is solving this QUBO task, and as part of the Neurobench system track, which I talked previously this week, we are also looking at QUBO benchmark. So this is the type of application that this chip would be able to solve. The QUBO benchmark can approximate this NP-hard problem called maximum independence set, which you may know of. So for varying graph sizes and densities, we'd be able to put this network into the chip. And since it's an NP-hard problem, we would probably not find the most optimal solution, which may look like this, but we may find a very optimal solution, which may look like this. And if you imagine the graph is extremely large, it would be most likely impossible to find the most optimal solution. So that's what this chip could be used for. Thank you.
Yeah. This is now one of the blocks that Leo mentioned, like a random number generator block for the QUBO problem, right? So
Right. So yes, Carmen and I were working on this, and so.
Oh, the video.
And maybe.
Let's share that video.
So we want to sample numbers from an exponential distribution, and one way to do that is called inverse cumulative distribution function method, where you want to sample from a uniform distribution and then pass it through the inverse function to get your samples x. So in hardware, to sample from a uniform distribution, we use a linear feedback shift register, and we can think that each bit that is coming out is like a coin flip. So we take 6 bits that are from the LFSR and feed them into a lookup table, which is approximating the inverse cumulative distribution function, and the output is then samples from an exponential distribution. And so we see that is like very log simulations of our sampling method, and yeah, it is approximating the distribution. Thank you.
All right, then one project that a lot of people were involved in the NIC group, I already talked about it during the demos yesterday, so I don't want to repeat all of that here, but that's, we are wanting to build a state space model accelerator chip in 22 nanometers global foundries technology.
And just to briefly recap, so we have a system architecture here that is sort of like a kind of standard digital processor with multiple different co-processors, but these co-processors are optimized to run state space models. So to implement exactly those operations that these state space models need. And so what you see here is a system that is going to be using this AHP Lite bus protocol so that the different components can talk to each other. There's similar to what we just saw for the random number generator. There's some block here that can approximate nonlinear functions to put in all of the different activation functions that these models might need. There's going to be a processor here for like pipeline logic. So because a lot of these models have some very specific operations that you need to do, for example, like combining two vectors with element-wise multiplications and stuff like this. So this is something that we didn't want to hard code because it changes a lot from model to model. Therefore, we want to have a programmable processor on here. And in addition to that, there's going to be a lot of stuff that needs to be controlled, like in terms of data flow, what data goes from where to where, and when to load what types of data. So there's also going to be a RISC-V processor on here that is going to be driving the whole show. There is a couple of co-processors on here that are really critical for this, where most of the actual computation happens. And these are this matrix vector accelerator blocks. So we have decided to go with ternary matrices because that's what Jason's MedMol free paper was using. We had a lot of discussions about it if this is suitable for other models as well. So we will just try to build like a chip for cool ternary state space models. And so in this architecture here, as I said, there is like 4 of these accumulator blocks here, and they are kind of really the core part here where most of the action happens. And so for those blocks, we did system Verilog, we did initial floor planning and placement. And what we found out is that this is really mostly about memory. I mean, this is not really surprising. This is kind of expected, but it's interesting to see the number. It's like really 93% area. And the computation that happens in there, that's a little byproduct in a sense. And so we started with a repository here. We will keep working on that. We have some initial Verilog code. We ran some simulations here, got some first estimates from synthesis. We then made a floor plan of this. So we have a rough idea how big this is going to be. And we have a good feeling that we can actually fit 4 of these in a reasonably sized chip, let's say 3 by 3 millimeters. And currently we are passing timing. These are all good indicators. Whether this will, like, it's a long road ahead, but currently I think things look sort of promising. For all of the other blocks, that we have ideas. We haven't actually started working on this yet. So there's more work to be done in the future. So we know that we want to use RISC processors. For this pipeline block here that is doing these element-wise operations, we're thinking to put basically a chain, like a systolic array of ALUs. So that if you have an operation that takes, for example, 16 operations where you want to add some vectors together, multiply with some constant, divide the whole thing by something, subtract something from that, that you can basically put this in a pipeline processor so that you have maybe 16 cycles of delay, but basically every cycle you put in a new value and the new value, an old result kind of pops out of the other end. So to accelerate this part as well. And for the nonlinearity, as I mentioned, we'll probably have some lookup tables and maybe some piecewise linear approximators here. Our idea to kind of build, like, how would you use this chip is not to put the entire model in one chip because that's really not feasible. But we think that the models are structured enough that we can put different parts of the model into one chip each. And then if we have a lot of small chips, we can just tile a lot of them together, build a big PCB, have like 40 chips on here, and then we can simulate, hopefully, like really, really large models pretty fast. So that would be really nice. So our plan from here is there's a lot of work to be done, as I said, like multiple times now. So we will have a first meeting like in 2 weeks, see who's actually committed, try to form stable groups across the different home institutions, and then we'll keep working on this. Our hope is that we can tape this out early 2025, because it would be really nice if you could bring some of these chips to next year's Telluride. So that's our plan. And yeah, that's it.
So this is the keyboard spotting project. As mentioned last week, we wanted to design, to implement an outdoor accelerator for a keyword spotting system to identify 10 keywords.
but by using ChatGPT to write the Verilog code, investigating the use of open source tools, and compare the implementation of this design across different platforms. Okay, this is what we want to do, but to have tangible results for by the end of this workshop, we started from a tiny spiking neural network to identify 2 keywords. Okay, why ChatGPT? The ASIC implementation, design, verification require a lot of resources in terms of expertise, a lot of time, and so a lot of money. So we wanted to explore the use of ChatGPT to accelerate the chip design and verification. So we started from the software. We used the L&T to implement to model a spiking neural network with delays by using the spiking Helbig digit dataset, and we achieved an accuracy of about 90%. For the other design, we started to breaking down all the system in smaller submodules, and we asked the ChatGPT to describe every submodules, and then test bench to simulate and verify these modules, and then the documentation. So this is in this slide you can see all of the submodules that we asked ChatGPT to describe. This is an example of how we asked to design, in this case, a leaf neuron. And these are all the modules. All of the modules, and you can see how they are all working modules. We implemented the design on an FPGA, and starting from the L&T network, we converted it on an NIR version and put it on Spinnaker 2. And we implemented the design on Skywater 130 nanometer using OpenLane. OpenLane is an open source tool that starting from Verilog files and configuration files, you can have directly the GDS2 file. And okay. Okay, and it is the 3D visualization of the GDS2 files of the design. So now we want to submit this design on Tiny Tapeout 8, and we want to compare all of the hardware platforms.
Need your help getting us with like an inhabitable version of one of these kits that we actually later on.
Yeah, real estate.
Yes, so this is just a very short overview over stream data processing with SNNs on Spinnaker 2. So there has been several projects where Spinnaker 2 has been involved. One was the keyboard spotting demo that Paula just presented, and another one was for space applications. And I just want to go quickly through this. This is basically the slide from the SP8 presentation, so I will go a bit more into the details there later. The initial idea was that we have some data source that we want to basically put onto Spinnaker, have a spiking neural network running there and reading back the results. But we wanted to focus on this part where we have the data on the host. So we really focus on this interaction between the data and the spiking neural networks. And yeah, so you can, we did this step by step. Initially, we just implemented with the Spinnaker 2 framework, the spiking neural network on there, sent in some data and read out the results. Then we did this from SNN torch with a trained model We converted it via the neuromorphic intermediate representation to Spinnaker 2. And then we ran the model and read out the results again. And this is what you can see here for two different applications. One's for the satellite and ego motion data that Giulia gave to us. So you can see here some stars moving in the satellite. And these are the spikes that have been provided as input to the SNN running on Spinnaker. And this is something similar for a keyword spotting application, where you have then this representation of the keyword over different input neurons over time in this direction, and you see some neurons spiking here. And yeah, this was just a short overview over basically this integration of streaming data into Spinnaker running in SNN. And there's been many people involved. You can see them at the corresponding blocks here, and also here for the training the SNNs. And yeah, this was a short overview. So yes. Okay. Might be Gary supposed to present? Yes.
Sure.
Or,
what do these slides look like?
It's gonna be a bit karaoke. So yeah, this is basically the presentation on Rakov LLM on different neuromorphic hardware. And so you've already seen this in the intermediate presentation. I will quickly go through this. This is the architecture of the Rakov model, which is a recurrent architecture which profits from data locality. And the idea is to put this graph that Terry created on Spinnaker. And there are different approaches that you can use there. One approach is that you can use such a scheduling approach that we already presented shortly in the intermediate presentation. So this approach would take a layer like the vector matrix multiplication, make this, thank you, Terry. You would then put this into a layer, which you would put on the scheduler and run it on multiple cores there in parallel, this kernel. Another approach follows a more decentralized step, and we got some first measurements on there. And okay, sorry. Yes, and another approach is a bit more decentralized. Maybe Terry, you can say something about this.
Sure. So like this basically, instead of go get distribute this task a bunch of cores, go compute that, then do this, then do this, then do this in the scheduler. Instead, just take everything and split it into little thin slices, and then have every core doing exactly the same task, but their task is the whole freaking network. That involves a lot more, there are a lot of communication between everything. We got the code implemented for it to actually compute all the math. We did not get as far as actually get it to call out to DRAM to grab the weights that it needs to compute to do the math correctly. Yeah. But progress.
There's still some work to be done. And this is the Lango implementation that has apparently also started. I thought you put in the slides, but you apparently didn't.
No, it's this group here, because they were working on taking this graph and converting it into Lava and actually running it on Luigi. And they got, they're just implemented all the components. Tried to figure out, some things were like, we'll leave this in Python, but we'll do a bunch of other things.
Okay, and here's some short comparison between running it on CPU and Luigi 2. So this is probably from the slide provided by the online participants, but maybe we can go through it quite quickly.
Yes, they're actually right there.
I don't know if you can hear me, guys.
Yep, we can hear you.
Okay, so yeah, just some small considerations on the work we did. So for running on CPU, we were able to implement the more simple blocks, and we would also be able to implement the macro blocks and actually build the full network. And the network is running, but unfortunately, we are not getting the correct output. We believe that the issue might be related to delays because this particular network has some, let's say, unbalanced branches. So we need to be careful that when the two branches merge, the correct data is getting in at the correct time. So we are trying to solve that, but by manually adding some delays in some branches so that we are sure that the data gets at the correct time, at the correct place. So for CPU, we have an implementation, but it is currently not working. It runs, but the output is not correct. We have not started yet the porting to LoiHi2. Some quick considerations. In LoiHi2, it already supports the dense connection, which means the matrix multiplication should be very easy to port. Some of the simpler blocks should also be portable to LoiHi2 because we can work with assembly, with microcode in the cores. The problem is going to start probably with the WKV block because this one is much more complex. It has exponentiation, it has a division, matrix division. So we need to think about that. And probably we will run into the same and even more delay issues. So yeah, our work was a starting point to have a working system on Lava on simulation to then start the porting to LoiHi2. Okay, that's it. Thank you.
Oh yeah, so talking a little bit about PFETs, I think we've all heard a little bit about PFETs throughout this workshop. There's been a lot of excitement about it. Kind of just motivate that a little bit. We heard Johannes mention earlier that kind of one of the main challenges in kind of circuit design and the system level design architectures today is memory management. How do you kind of deal with that? So basically this top two pictures show like your traditional CMOS device. This is an N-type device. And basically you have these four terminals. And basically the output current this device has is a function of those four terminals kind of directly. So there's no real way to store any kind of state with this type of system. So typically we combine multiple of these devices or some parasitics or things like that in order to store information in these systems. And this is kind of one of the main drivers why we're looking for kind of these more exotic devices. So down here we have a PFET, where basically they put in some extra materials down here. They basically add some ferroelectric material between the gate and the actual device. And that gives you these kind of IV curves where you can actually program the threshold of the device, allowing you to kind of store information. And basically you can detect that information depending on how the IV curve is structured here. Basically where you are kind of left and right on these curves sets what information you've stored in the device. Next slide. So yeah, one of the main questions we're kind of looking at for this workshop is how do we actually build these devices? Next slide. So basically we have two available models. One was developed by the Fraunhofer team in Dresden, I believe. Or yeah, not the honest, but you know, adjacent. And another model from Notre Dame. So we have both models installed here locally and they're running in cadence and we were able to do simulations and kind of experiment with these devices. This is kind of a rough idea of what the model looks like. It's a combination of Verilog AMS and a macro model of kind of your ideal circuit components. Looking at the next slide. This is kind of just a basic, this is really hard to read, sorry about that. It's basically a single device here where you have the drain set from B pulses and the gate set for E pulses. The bulk and source are both grounded and kind of set constant. For the next slide. So,
the lights there.
Perfect. Yeah. So basically we have a set of pulses here and I'm going to kind of show what we're doing for this PFET device. So we start with a read pulse. So that read pulse is basically a kind of normal drain voltage with a small, for this process, relatively gate pulse. And we can see the output current is relatively small. So this device is basically in the high VT state. Then if we go to the next slide, we're doing a programming pulse. And so you can see here we have a very high gate pulse. The drain is grounded and you can see these little lines coming down. Basically, this is several simulations kind of stacked on top of each other, and we're varying the width of this programming pulse. So on to the next slide. So after programming, once we read this device, we kind of apply the same set of pulses here, but now we get these varying current levels. And this basically represents kind of how much we shifted the threshold. So from the original plot that I showed, we're kind of showing where and how far we've shifted that IV curve. So the next pulse is our reset pulse. So we apply a very large negative gate pulse. And basically you can see on the next read pulse that this completely erases kind of all this threshold shift that we applied in the device. So basically kind of what we're showing here is that we're able to kind of set the device into multiple states, basically indicating that in this single transistor, we can kind of store information, which is much denser and kind of a very interesting concept for modern architectures. Moving on to the PFET side of things, basically in the schematic now, instead of applying the pulses,
all 4 terminals have a constant DC voltage, and we see a bunch of nonsense, basically. It is oscillating between like plus and minus 200 microamps. So basically this model is doing some crazy stuff. Not really working. We had a bunch of convergence issues. You can see here the tool is complaining about 0 diagonal Jacobians and things like that. So we're still kind of messing around with this and getting it to work. But the NTET sims are very encouraging. It kind of just lets us know, like lets us prototype kind of what we can do with these devices.
I like the auditory group.
Maybe that's what I get. Yeah, so as I mentioned. So kind of the more interesting question for us, since these are very experimental devices, is how do we actually build them? Like we want to get them into the lab and actually measure them. So this is kind of a layout of a single NTET device. Basically, it's your standard CMOS device. And basically what GlobalFoundries has done is they basically let you modify the PDK. You can't really read this, but that says FEFET, which kind of believe me. And basically you just draw
very dark and
yeah, you draw basically a rectangle. For those of you familiar with layout, it's basically kind of just like a threshold mask over the device. Then GlobalFoundries sees that and says, "Oh, you wanted to build a FEFET, and you're ready to go." Yeah, so that FEFET layer. So basically, these are the rules for that FEFET mask. For those of you who do custom layout, you're kind of familiar with these pictures. Basically, the idea is you can put as many transistors as you want in here. Those all become FEFETs, and there's various spacings and stuff that you have to check. So kind of the current status is we have the PDK set up with the FEFET addendum, as GlobalFoundries calls it. We're still working on resolving some issues with the FEFET DRC layers being skipped. Basically, when we run our DRC checker, those rules that I mentioned on the previous slide aren't actually being checked. We have some individual devices at GlobalFoundries for measurement, and we're starting to kind of plan our test structures. We're targeting an MPW in either September or December later this year. October, apparently. And we're looking for a collaboration. So if anyone's interested in actually building any test structures with these devices, contact us on Slack or email. And if we all know Andreas or myself, so yeah, feel free to get in touch and let's try to build some cool test structures.
Right. Then. Awesome. Yeah. So as you probably know, we thought about this thing called NEAR last year, Telluride, and it kind of became a thing, except there's a big missing piece here, which is a big of a Thor thumb right here, right? We have to gray that out for the videos because we're not doing analog mixed signal systems. So obviously, sorry, I will put that. Oh, thank you. So thank you. Yeah. So obviously, this is what we've been wanting to fix. And I remember some of Jennifer's talks, and I realized, oh, we kind of think similarly. Like these building blocks we're talking about, these ODEs. That kind of exist in analog. Like, is there some way that we can marry these two things? So, a very quick idea about what Jennifer is doing. I mean, feel free to
go ahead. You're doing great.
So Jennifer thinks in signal flow graphs where you have some kind of IO pad, you have a low pass filter, and then some kind of hour buffer. Right? And you get these very nice gain over frequency curves. And funny enough, NEAR thinks in signal flow graphs. So we can rewrite this as ODEs, and then we can work with this and optimize it. So literally, this is something we can work with and optimize in our simulation, and ideally dump into FPAs. So very preliminarily, we just simulated this ODE, and you can see that if you give it different pulse inputs here, you get different responses for different time constants. We can kick it a bit more, and we get a bit more output. And so yeah, I think that's pretty much, so the idea basically is simulate all these neurons and ODEs and even make more complicated circuits like Winner-take-all, and then we can dump them directly on an FPA.
So I think one of the things that comes out of all of this is the fact that there's a number of different pieces of tools that are getting kind of pulled together to deal with neuromorphic structure. And there was a good discussion, just like the original part of neuro is to say, can we actually pull things together?
Exactly.
And I think I think there actually turned out to be some tool discussions and discussions also with with Ningo and a few of the other things where all of these things look like they will integrate together. And so this is just the beginning of how do we start really building the sort of higher level tool framework for a lot of these designs.
We're in the stone age of analog technology. Okay, a little bit. In the medieval. Anyway, thanks for your time.
Yeah, the answer to you want. Kind of a thing. What do you mean by that? Just got accepted. Just got accepted to Naked Communications a week ago.
Okay, wrapping up for the NIC group. We have already mentioned there's going to be a lot of work coming up after. So we want to keep discussion groups going. We will send around some like contact forms, whatever. We'll try to get everyone who wants to stay in the loop. We'll also try to do a better job of engaging the online participants. It's a bit difficult to do this in the setting here because it's all a bit chaotic and things are changing spontaneously. But we will work on this remotely from our home institutions. We have a couple of different tape outs that are planned, so we have a busy schedule. Let's see how many of these we can actually meet. We'll find out. So there's a Cubo tape out planned already in September. For the state-based models, we're thinking realistically maybe early 2025. And for the FIFAT stuff, we learned October, so it's not September, December. So we'll be busy for the next couple of months at least. We are looking forward for next year. I'm not sure, Shantanu, if you want to say something about next year's topic area for next.
Yes, so the next year, the topic would be sensing and perception. There are 4 themes that we are looking at. One is vision, audition, olfaction, and the fourth one, extrasensory perception.
Okay, so for the online people, yeah, vision, what was it? Vision, audition, olfaction, and everything else. So, okay, we cover everything. Okay, so with that being said, I think on behalf of the actual organizers of the NIC topic area, I think I want to say we were very happy with our participants. It was nice. We had great discussions. We took forever to get started, but it was a lot of fun. I think we also learned a lot, and I also would like to say specific thanks to our staff team, Mike and Paula, who not only worked on a lot of these projects, but also provided the infrastructure that we relied very heavily on, and the glucose that we needed to keep working on it. So thank you very much. Final words from Andreas?
Oh, I think this is really, thank you all the participants. This was exciting to come to a workshop that started really also about hardware, bring back hardware design and actually do something in 3 weeks, which is actually pretty remarkable. So thank you for all the people that really been
That we yield the remaining minutes.
Thank you. All right. So next will be language and thought, but let's take a 10-minute break so that people can breathe. So, in 10 minutes, we will start again, language and thought.
Here we are at the final presentation of the inaugural language and thought topic area at Telluride 2024. Thank you everyone for your vigorous participation. We were a small but mighty group in terms of the participants that admitted. I feel like we got a lot of folks who really engaged outside of their comfort zones in ways that was really inspiring and exciting to see over the course of this workshop. So thank you for that. Got a great list of people here. You're going to be hearing from many of them. Those of you who have slides in here, get ready to stand up and present. This is my only overview slide. So we came into this with a very ambitious scientific agenda. Right now, I think it's pretty obvious to everyone that a lot of the field of artificial intelligence in the research and kind of commercial spaces is going through this concept of language as a driver of agency and reasoning and an analog to thought. And so we decided that we were going to come in here and figure out where we could push the boundaries. You'll see that we kind of largely self-organized into a handful of different themes. The cognitive processes that are represented in an AI, the action selection, planning, the reasoning through problem solving, was well represented. We had a very strong focus on making today's and tomorrow's AI much more efficient and adaptable. I think this has always been one of the obvious hallmarks of the areas where the brain has an awful lot left to teach the concepts of machine cognition. So we spent a lot of time thinking about what might be out there waiting for us to bring it into the field of AI. So neuromodulation, memory consolidation, and kind of the learning of procedural memory on how to teach machines new things in an online way. And then lastly, there's the social cognition and knowledge representation, this ability to kind of observe the world around you and manipulate the knowledge that you possess. This is something that modern AI is actually quite bad at. and it's something that we were looking to advance through the ability to perform knowledge editing, this kind of ability to control and interpret symbolic representations inside of the LLMs. And lastly, kind of the ability of things like LLMs to create some notion of theory of mind for interacting with people while building up models of the other agents around them. So I know Jason would be really disappointed if there was no AI generated graphics, so I asked just to kind of level set a little bit of where we are with today's AI, I asked it to take a look at my picture from my cell phone of this slide about 10 minutes ago to create a minimalistic, extremely corporate efficient cover slide. And so here we are. This is kind of what you get out of today's AI. 30% nailed it, and 87%. So okay, this is where we're at. This is what we're trying to improve upon, and you'll get to see over the next 37 minutes how far we got with that. Wow. Okay, and with that.
All right, right, so we were interested in replacing a recurrent neural network with a vector symbolic argument algebra statement. And we tried using VSAs in a standard model as an input-output format. Last time it worked when we took in VSAs but sat out one hot. It didn't work with VSAs. We fixed this. We haven't gotten around yet to replacing the recurrent. Oh, sorry. We haven't gotten around yet to replacing the recurrent network with the recurrent SSP structure. Although, as we showed you last week, we were able to use that recurrent SSP structure to predict a metric, and that was to say to learn online to predict the Mackie Glass data set. But one of the things that we did while we were trying to figure out the character stuff is we started doing model predictive control in trajectories represented using this recurrent SSP thing. So we took in inputs, command sequences, and initial states. We fed through a population of neurons in Norse. We predicted the VSA embedding of the trajectory. And then we also took a value map that we embedded as a vector. So then all we had to do was feed in commands into this network predictor trajectory. And then with one single dot product, we evaluated the entire model predictive control interval simultaneously, which turns the complexity of it from linear in the number of sample points to linear in the dimensionality of the representation, which is constant over the lifetime. That's a big improvement. What we're seeing here on this graph is the predicted value using our VSA embedding in the linear map, and then the true value of the trajectory by navigating a vector space, and it's got a correlation of 0.9 or a square root of 0.9. And then this video just shows the blue dots are the 2D embedding of the commands. The trajectories are the output of following these commands, and then the color background here is the value map, and what it's doing is searching through the space and finding progressively better trajectories. The nice thing about this VSA representation is, even though this is designed for a metric space, the representation doesn't require a metric space, and we would hope to be able to try and extend this to language so we can start talking about planning and control in language spaces, which is how this ties back. So
slugs go up.
Yeah.
Yeah, but that's I think that's all, right?
Yeah, I think that's all.
Okay, cool. We were interested in, I guess, as Guido was talking about earlier, in increasing the efficiency and adaptability of large language models. We were really inspired by animals and natural intelligences that can just rapidly adapt their behavior as well as their memory to a particular context. And so we had a large group of us exploring like a variety of different strategies in that general direction. And so we know that neuromodulatory systems, specifically governed by acetylcholine, dopamine, serotonin, and noradrenaline, are positioned to rapidly restructure the dynamic, like the global brain dynamics. And so we've been guided by how the brain can compute useful functions despite huge changes in dynamical regimes in which it operates. And then the second question is how we might leverage these mechanisms to produce more useful or efficient agents.
So to sort of flip the problem on the side, so we decided to make, like, you know, if we could make a experiment in an RL setting where we probe the broad question if neuromodulation is essential to learn, you know, ethologically relevant tasks. So we created a Telurun, the name's from Catherine. It's kind of a game, and the idea is simple. So we based it off of a water maze task, which is essentially a foraging task. So the mouse has to probably go to those green spots to get reward. But the twist here is that there is bear, which is also hunting you down. So the task now becomes twofold. You have to go to the reward locations, but you also have to avoid the predator. To sort of do that, we kind of hypothesize that you might need to have some sort of memory to learn how the predator might behave. And you also might need something like neuromodulation. So if you're foraging versus you're being chased, you kind of need to sort of change the dynamics of your network that's deciding which policies to take without changing the underlying weights, which is kind of like a very Eve Moder-esque view of neuromodulation.
What happened in the mouse meets the bear?
Sorry?
It looks like the mouse, you didn't get eaten by the bear.
It doesn't get eaten,
Yeah,
it's mauled
it's,
slightly.
yeah. If it got eaten, then the task would terminate. So it's kind of like, sorry, a sprites thingy that I need to realign. Yes, we want to especially thank Jules, who has been inspiration for this task. I personally, so I live in California. I've never seen a bear. The first time I saw a bear in the US was with Jules. And he's been seeing bears a lot. He's our bear tamer, so this is a homage to him. But yes, so kind of the same idea. And maybe in the interest of time, just going to results. Far left, it's vanilla DQN, and it's hard for it to learn the task. It kind of finds like a local minimum where, you know, it's like, I'll just go to the edge, the bear's not going to chase me, but it does not go to the safe houses where it might get reward. On the center, there is, we have incorporated an LMU. Oh, like a pointer, there it is. Center, there is a LMU agent that's a LMU unit that's sort of guiding the behavior of the agent, and we are using this idea of conceptor, which Catherine will go into. It's kind of like an adaptive filter, which kind of lets us switch dynamics between two states, like, you know, foraging versus chase, and you do that without changing underlying weights. And you know, you kind of also see some interesting behavior. So if you freeze the bear, the network kind of learns that, hey, you know, I shouldn't go too far. I can just settle down here. So, you know, it's kind of a settler's mentality. But yeah, so it's kind of an ongoing work. We don't kind of want to make broad claims, but it does look like neuromodulation could be very interesting for RL. Yeah.
So one mechanism that we thought might be useful for an AI on this task was a phenomenon that happens in the hypothalamus. So during non-stress conditions, we see low firing rates in a population of cells that launch the endocrine response to stress, that dump cortisol in your blood and allow you to react more quickly. But during stress, they have very high firing rates. And so we hypothesized that this switch in the dynamics of the system might actually be leveraged in some way by the body or by the brain. And so we showed that we could decode different functions depending on the level of current that we injected into the system. So artificially augmenting the baseline of levels of firing rates. We can see that for low levels of, for negative current, we're able to compute one function of the input, and then for high levels, we can decode another one. But we weren't sure if we could do this online, if an agent could actually learn these functions in the context in which they're being exposed. We'll have to hand things over to Martha to talk about that solution.
So we continue exploring this idea of current injection into a population of neurons. So essentially the task is quite simple. We have a population of neurons, some current injection here, and the task is this population have to learn identity function and the different states of stress. So we first try to do that with a simple delta rule. So you can see that the current injection is going to change every few seconds. So we have like 3 different states. So during the first part, the population can learn the identity. Then when we change the state, it already learned, but when we change again the state, it forgot what the population saw at the beginning. So what we did was to record the activity of the population, calculate the variance, and target the neurons that are not saturated. So that allows, and use this information to modulate the learning rate. So we allow a faster learning for the neurons that actually matter in this kind of task. So we can see that for the same setting, the network learned for the first task, second task, and it remembers what it saw previously. So you can see a reduction in the total error. So.
And so a final thing that we thought might be useful for this is to be able to modulate the dynamics of our current memory. So we combined the idea of conceptor networks with state space models and did an implementation in Mango. So at the bottom here, you'll see that we have some input, and then Nicole and I coded it up so that we would have a 1 second delay. And then we can, at some point, this value here will actually change, and we'll see that yeah, here we go. So we've pushed that dynamics into a different part of the state space. So we could use this information to potentially pick out different contexts in which we might need to learn different policies. Yeah.
And that mechanism was actually what was used in the reinforcement learning task. We've had a lot of fun working on these different directions of exploring neuromodulation, but there's a lot more work that we want to do after the workshop is over. We want to continue using this metaplasticity learning rule that Marco presented, applying it to different tasks, including in the reinforcement learning setting, combining it with that other work that we've done. We also want to work more on this idea of conceptors as a way of modulating these recurrent dynamics. So the conceptors, that was the way we, that was that switch between the different regimes, dynamical regimes that Catherine showed. And that was also the switch between the chase mode and the settler mode in the reinforcement learning task. Right now, that switch is just sort of a random projection of the dynamics in different parts of the space. So it's not like it's learned, it's not controlled. And that's the main thing we want to work on next, is actually learning a way of switching the regimes in a way that's useful, and actually have a meta controller that's making that choice. So getting into the realm of hierarchical reinforcement learning.
All right.
Great dreams.
So this project was about improving the ability for LLMs to reason on problems by taking advantage of the fact that they can generate a lot of sometimes nonsensical reasoning paths, which may have elements that are useful for task abstraction. So kind of in contrast to in-context learning, where you will inject a few exemplars into your starting prompt to help a model do a problem it's never seen before. What we wanted to do is take examples of the model performing the task properly and then compress that into a task abstraction that could be sort of expand the generality of what a model can actually reason over. So here's an example of like if that worked. So you have a typical tree of thoughts on the left. So this is like a middle school math reasoning problem where Jenny has $2 and she gets paid overtime 50%. How much does she make after 6 hours of 2 hours overtime? And the model will make hypotheses. At every step, we check for validity. And in this context, validity is only, did it make a guess? And if it didn't make a guess, I can't really make a judgment call on if that particular reasoning step was valid. But if it does make a guess and it's wrong, I can check it and say that was wrong. And then I have to go back up its tree to its previous hypothesis generate more hypotheses, and continue on until it eventually gets it right. So you can imagine, once we have found a reasoning path that results in a valid answer, it has solved the problem, we can then take kind of everything it said to itself and then distill that or start to reason further from there in a less constrained way. This is the dreaming or the hallucination as a feature, to arrive at something that may help you solve the general class of problems better, but it's not necessarily useful for this problem in particular. And the hope was that we would expand the number of problems we could solve, so increase our accuracy over a large set of problems, or become more efficient on particular inferences. So one of my favorite things that came out of this actually was from the demos, where Cohen asked a question of my demo about, this was the question, so apples 40 cents, bananas 60, grapefruits 80, how much is a pear? And to save you some time, the key insight in this problem is that solving this problem involves counting up the number of vowels in each thing. So we've talked about this before in the workshop, but the reason this kind of problem is hard for LLMs is because LLMs don't have letters, they have tokens. So it doesn't know that pear is 4 letters necessarily. It could be 2 tokens or 1 token or 3 tokens, so it can't count. However, the most interesting part about this one was that we accidentally put the wrong answer into the checker, and it was still able to find the answer. And when you look back through its reasoning, it makes some like logical leaps, which is this hallucination. It says like, well, all the fruits are multiples of 20 cents. Therefore, I'm just going to guess 80, which was right, even though it should be 40. And even if the answer was correct, it oftentimes was able to solve the problem, but also with faulty reasoning because it can't actually count vowels. But it did figure out that perhaps it's the number of syllables in pear, which is 2, which is wrong. But it basically had to do this game with itself where it knows the answer has to be a multiple of 2, and the only thing it can think of is like maybe it doesn't know something about pairs. And so those types of logical leaps are at first look kind of invalid, but not useless in the context of learning. So we tried to take, I took 10 examples from GSM-8K, which is middle school reasoning. We had the LLM solve it and then try and distill that into task abstractions, re-inject it into the prompt, and then do the test set again. Unfortunately, it doesn't work. And I'll explain why in a second. But we are happy to see that our tree of thoughts method outperforms Meta's kind of benchmark for their Llama 3 model by about 5%. And it would be a little bit more efficient if I actually made the histogram of how many inferences it took to solve the question. So this is why the task abstraction doesn't work. If you look at the problem solution, if you could read this, it would be pretty valid. And then you ask the LLM, like, can you tell me what kinds of reasoning you used to solve this problem? It sometimes just says like, I don't know, data APIs. So basically the upshot of this is that LLMs are pretty bad at reflecting on their own reasoning from their own examples, at least in the way we've done it here at Telluride. So kind of the next steps here is what different representations or intermediate representations can we utilize that perhaps get deeper into the knowledge representation of the model versus its token representation, which is is basically like going from a representation to a discrete back to a representation back to a discrete to try and get past that task abstraction instead of just living in continuous space. Trade soups. Thanks.
All right, thanks Tim for setting us up already. So we have a couple slides that we'll just repeat from last week. We can go kind of faster. So just to remember, this is the general idea. We have these like state soups, which are just a bunch of hidden states from state space models, because the hidden state in the state space model encodes all of its input history and all of its kind of like skill or whatever it has looked at so far. And the idea of state soups is that you can combine these by just averaging over the states.
What's happening? Laser pointer, so it's part of the recording.
Oh, right.
Yeah, thanks.
Yes, these hidden states we average, and then the idea is if each hidden state encodes, for example, a document, you average all of those, and then you have access to all the documents in some kind of way. Yeah. This is what I showed last week. So we give it some kind of context, which is Owen likes nuclear weapons. We extract the hidden states, and then when we ask the query, what does Owen like? We inject this hidden state that encodes the sentence Owen likes nuclear weapons, and then the model talks about Owen liking games because he likes nuclear bombs, something like that. So we played around with that a bit more, and what we managed to get out now is if we play a little bit with the interpolation factors, we can get the model to output this, which I don't know if anybody can, I mean, yeah, this is Japanese text. Anybody can read it, but DeepL says that it says Owen likes nuclear weapons. It just so happens that sometimes when you interpolate in the state space, you just get into the Japanese speaking region of the state space, which is a bit of an issue right now. But yeah, we're working on that.
So we created neuromodulation with like a sentence.
Exactly, yeah, you can look at it that way. So there are some graphs of like how well this interpolation works in different layers with different interpolation constants, which looks like there's actually trends, but then when you put the standard deviation on it, there's no trends anymore. So yeah, we identified two problems, which one is that this like state swooping gets the model into a regime of unexpected behavior because it just hasn't been trained on these kind of interpolated states, so it doesn't know how to work with them. So what we want to do as the next step is to fine-tune the model on interpolated states during training so that it can work with soups. The second problem is that Mamba is pretty stupid. So even if you just put the context, like information into the context, like a document, and then you ask it a question about that document, it doesn't use the document just because the instruction tuning of Mamba is really bad because like some random person did it, and Mamba itself, the model is only pre-trained, so there's no fine-tuning, instruction fine-tuning. So we should improve the instruction fine-tuning for Mamba, or we could use recurrent gemma, but like we said last week, recurrent gemma has attention blocks, so we would have to distill them into SSM blocks or some kind of magic like this. Here's another, not very significant finding of the correlation, but yeah. Next on to the knowledge graph.
Yeah, so we want to do RAG, right? Retrieval. So imagine you're this stockbroker or a stock trader or Warren Buffett. You read all this information on the Financial Times or economists. You have knowledge about all these companies, top companies. So what happens is that all these pieces of information are stored in this hippocampus, and your brain try to organize through the neural cortex, and then they have very efficient way to retrieve them. I'm just bullshitting. I have no idea how it works. In the brain, I'm not a neuroscientist, but as a computer scientist, I can build a graph so that I can retrieve information very fast. So what we used was this knowledge graph, and it's structured in a hierarchical way. It's called a hierarchical navigable small world graph. So starting from some node, you can traverse to the nearest neighbor.
I can point this here. You can point there, and I can point.
Okay. Traverse from the entry point all the way to the nearest point. So suppose you have a query that lives in this embedding space close to here. You need to find the nearest neighbor, which is this. So you go all the way from the entry point using a greedy search algorithm. Because the graph is organized in a very structured hierarchical way, so you can very quickly find the nearest neighbor, and you can retrieve the top K nearest neighbor from that graph. And the way we get embedding is to use this sentence transformer, which is trained to align the query embedding to the embedding of relevant document in the embedding space. And the data set we use is so-called financial RAG, which has the top 69 companies information. And we try to test that with our language.
Yeah, we basically set up like a demo to see how well it works to encode queries and documents with Distillbird. And we also visualized the graph that was constructed. And then we just asked questions about the different documents that were in the graph, and it worked pretty well.
Yeah, this is computing the embedding of that prompt and then just using this graph search over the vector representations of these different pieces of information to retrieve the text that's shown on the right there.
And the next step to link this back to the state soups would be, for example, to use this small BERT model to index the query and search the graph, but then at each graph node, besides like instead of, for example, the whole document, you will have the state soup that you could then plug into Mamba or a larger model, so that when you search, you actually use a small model and it's fast. But then when you want to retrieve and compute like the actual answer, then you can use the large accurate model.
And you don't have to pay the same price of recomputing all of the context because you've souped in the information. So it's retrieving stored knowledge as opposed to kind of retrieving the base, text that you then need to re-encode and turn back into, which I think is kind of part of it.
And the whole thing is basically for free because you only have one averaging operation. Whereas with the self-attention block, if you add stuff into the context, like the longer your context, your inference cost grows quadratically, and you don't have that with state-based models. So that's the whole point.
Yeah, we have a good way of us organizing this information and searching through it, and just need to work more on how to soup it in a way that's effective and to train a model that can actually make use of that information.
To answer in the same language that you prompted.
Hi, everybody. So this group was not really a work group, more of just a discussion group, but trying to understand the problem space of the ARC prize, which is a $1 million prize for a test of artificial general intelligence. And the problem is really just that you're given sample puzzles on a square grid, perhaps 2, 3, 4, 5 examples of each problem, and you have to fill in a grid with an answer statement, if you like. And yeah, we didn't make any progress on this, but understanding the problem is really interesting. And I would recommend anyone working in large language model space, go and take a look at this because it turns a lot of your preconceptions on their heads. They're basically pattern recognition problems. They're supposed to be culturally independent. Whoever set them up obviously didn't realize that color space is a cultural concept, but that's fine. The problems are that there's only 400 example problems, and all the test problems are outside of that space. So you don't have a massive database of problems to learn from, and all of your answers have to generalize outside of the input space. Yeah, and so I mean, so far state of the art is about 40%. Human response on this is 85%. So it's a really good problem in the sense that we have really terrible solutions for it at the moment. So we didn't really, we were just trying to understand the problem. I was really interested in tree of thought as a possible avenue to make an approach to this, although the competition itself requires offline solutions. So that's going to be difficult. But yeah, recommend you look at it. It's very thought provoking. Thank you very much.
This is another discussion group that I will represent since Carrie went home after the second week. You'll notice that actually a lot of the interested parties went home after the second week, and so we had some adaptive rebalancing as the workshop went on. But this was around the question of whether or not the exposure to language and human behavior thereby is enough to kind of build up a theory of mind that would allow an agent to make predictions and to build accurate models of the internal thought processes of other agents, that you could do more to kind of understand and respond to social dynamics in multi-agent types of settings. And so there was a lot of initial theorizing around kind of how we might measure this and how you might test it and how you might train it into systems. There were some interesting lessons learned, which is that if you kind of look across the ecosystem, a lot of people have studied this within the context of LLMs already, but it tends to be a lot of fairly low quality data sets, which I would say that most of our groups ran into. If you kind of look into the granular level data that is being used to evaluate all these systems, they tend to be rather disappointing. And so kind of understand that the metrics and the metrics used to measure these models today are far from a perfect measure of kind of like the intellectual capabilities of a model. We began some investigations of multi-agent RL, kind of recognized that was by in and of itself its own super 3-week project, and that kind of focused on the bare chase game as an alternative. But that this type of thinking of like how do you probe and instrument a model and the ways that you might inspect, the internals of a brain is still really needed and useful here. So there's still a lot of work that is required in kind of bridging the interpretability communities together with the AI safety communities, because right now I think people are reinventing a lot of the tools that might be necessary to perform this type of work. And I think that a lot of people in this room might have some of those tools in their back pocket. So it might be worth thinking about how would you study these types of networks in a way that would allow you to make contributions into the AI safety and AI interpretability and control debates, which are very vigorous right now. All right, and we also have a bunch of investigation on neuromorphic hardware. Yeah, come on up. Yeah.
Slide from the first round of demos, but I can say that we've done some improvement on implementing state space models in superconducting optoelectronic hardware. There's going to be some really long acronym, obviously, to make that sound cool. But the point is that we have a system that has leaky integrators through superconducting circuits, which are super fast and scalable, and moreover, we can communicate with photons, which allows for really big scaling, but then we have to figure out how to deal with spikes. However, we do have like dendritic trees in this hardware, and those dendritic trees filled with leaky integrators basically can operate as sort of your latent state space in your model. Look something like this, where these would be your dendrites, and you just map your input to the whole tree, and then you learn just this readout mapping C, and we're using the, I think I've got some equations here, just the LMU for now. I think there's a lot of work to be done investigating what would work in these contexts, but just the LMU equations for the A matrix and the B matrix. Finally, I haven't put in new plots here, didn't know I was presenting, but we've improved this quite a bit actually, and now this orange line follows this blue line really well. The key was actually, and this is interesting, is just to lower the leak rate so it more tightly follows these lines here. However, when it comes to the classification tasks that you see here, separating anomalous and regular heartbeats, actually the leak integrator, which with a longer time constant, which looks less good, is better for classification. So maybe there's something about making it a little more separable and smoothing over the features in a way that is easier for this readout mapping to learn. I think that's all I have on this. And here's some plots if you teach it to either spike when you see an anomaly or not spike when you don't. And it happens to work. Thank you very much. It was a lot of fun learning about SSMs, and all the other work on the topic was really inspiring. So thank you.
Okay. Perfect. All set. Thank you.
So hi, we are a side group. In the group is Leo, Leonardo, Vilma, me, Soraya, and Terry is helping a lot with us. So as I said another day, just a quick introduction. We have this router in Chile, and we can record the ganglion cells with a multi-aligned electrode that is here. We put the retina of that rodent here, and we can look how is the responses of the ganglion cells, given that in this case this stimulus, this is a white noise stimulus, and this is the neural response of the one in particular cells. So we wanted to do is, given that this stimulus, we wanted to make a network who can learn how is the responses of the retina for in particular stimulus. In this case, as Miguel said, is that winders.
Okay, in this work, we try to replicate the natural response of the one type cell, the retina. We use the LTM model, more the leaf rate, and we use the white noise for the input signal, and the LTM encode in different frequency and the leaf rate learning and evaluate this response the retina. And the next slide, we have the result of this model.
Yes, like it says, we first divided the data in trained data and validation data. We put in the Nego systems, we put the white noise, and we have this result, 95% of cosine similarity. And we say, oh, it's okay. and try with the validation, and we have 42% of the response. And we need more. We need more. Maybe change the architecture, or we put more hidden layers in our architecture. Next slide. We have the next conclusion. It's although the LDN can partially replicate the neuronal signal of the retina, it still requires future adjustments to improve its generalization capabilities.
So with the future plans is we wanted to that network really learn for a different type of sets. So we want to improve the model to increase the score and use fewer parameters because we had a lot of neurons now, and explore different kernel size of white noise. That is, for example, I'm going to go back. This is the receptive field of the neuron, the responses to the stimulus that is white noise. That just with the most high values pixel of the receptive field. But we are wondering if maybe this shape of kernel is not enough to have a good validation. So we wanted to explore if we can make I don't know, maybe we can put a biggest white noise, not using the whole matrix, but a biggest one when we use them. Maybe we can increase the score. And after that, we just train it with one neuron, and we wanted to train it with a largest number of neurons. And we've made that before with a LSTM model, and we have this kind of result. And if this network can work that the responses of the retina, we wanted to do the same thing that we made with LSTM. And that we made is really separate the neurons, the different kind of neurons for the shape of the receptive field, the form of the neuron. We look at what neurons have the similar patterns of that response. And we had 7 different groups of neurons. That is the color of each receptive field of each neuron. And we have the most. We classified with the most group that it has the largest number of neurons in each group. And we just only with training with white noise that we had that if we're training with white noise, and after that we put a natural image. This is the natural this is where the goose live. So this is the natural environment of the goose. And we can see that this is each color is a different group of neurons, and we can see that each group can replicate one part of the real image. For example, for this frame, here is the horizon line, and each group can replicate one part of that horizon. And in the frame 44, this I don't know if it's here, but this is a tree here. And for example, there's another group of neurons that can look at the shape of the trees. And in this time, there's another tree too in this frame. And this group of neurons, if you can see that it's like a look in that shape of the trees. So we wanted to replicate that with the Nengo model if it works in the future. That is, thank you.
Space group can be up next, please.
As you can see, I don't think we actually had that much time in hot tubs. We're actually busy up doing other things, unfortunately. And it's going to be an interesting, quite packed presentation. So I'm going to keep the introduction very short. And you'll see there's a whole bunch of things we're going to talk about on characterization of satellites, processing data, capturing data, control systems, and also some of the general ideas around how we work with and produce and process the data that we captured as well. But I think that's what I think is really interesting about how our group formed is that it's really driven by an application. And I think one of the things we have to be mindful of is that if you're looking at bio-inspired solutions, you're actually kind of sometimes starting with the solution and then looking for a problem. So sometimes it's good to actually bring the problem up front and say, here's a problem, here's some real data from the problem, here's the constraints of that problem. Take what you're doing and see how you can optimize and fit it into that. So a lot of what you're going to see today is about that. And I'm just going to quickly talk about some of the data we collected, because we collected a lot of data. As Alex says here, we're definitely winning. And there was actually a lot of method to how we did this. We evolved over time. So really on the second or third day of the 4th of July parade, we tried to record the F-16 flyovers. We sent 2 people, different places, tried to figure out how do we coordinate all of this. There were technical challenges, but there were communication challenges as well. Then we moved on from that to looking at fireworks, see if we could do the 3D reconstruction of fireworks. 16 different places, lots of cameras, really, really exciting, tons of data. We then moved on to that, to looking at shooting stars and meteorites, having teams looking up at the sky in different places. Now we've moved on to GPS synchronized devices to record the data. And finally, we moved on to lightning, which was much more dramatic, much more exciting. And Alex will show you some of the results from that. So with that, I'll move over to Alex to start talking about some of the data that we captured.
Thanks, Ray. Okay, so one of the first things we set out to do with a massive group and 6 cameras in the mountains, try and record the fireworks from different perspectives with the end goal to do a 3D reconstruction of it. We generated a lot of data, something like around 300 gigabytes. It turned out to be quite a lot of work to just render to get a sense of whether the data was any good. So we built this little timeline to get a sense of when each group, sorry, Toby. Can I get some? Okay, so
L.
L.
You just took it away.
L again. There we go. Okay, so the bottom axis here is time, and the axis here represents the different groups. So once you have that information, you can find a nice time window where all the groups were properly recording. The next step to do 3D reconstruction is to get a sense of where the cameras were in 3D space. Pretty easy because we can simply use the GPS coordinates that we recorded. You also need the 3D orientation, and that's much more difficult. So to do that, we downloaded an elevation map to try and realign the field of view with the background features. So that map was perhaps half a degree by half a degree, a nice square map. And there's actually something incorrect in what I just said, as we'll see in 2 slides. The challenge really is to find a map that is big enough, that it's precise, but not so big that it crashes the software. So we've reached the point where we realigned the sensors. It's not perfect, but the data is out there. So if anyone wants to move on to the next step, which we haven't done yet, that is 3D reconstruction using different sorts of algorithms to see what we can do there. So whilst this was happening, we also tried to replicate the same experiment with lightning. The problem is very similar. Deploy teams in the mountains, try to point the cameras at the same thing. Because we didn't know where the storm would be, we agreed on letters to represent different potential directions and try to all record in the same overall direction. So we had 3 somewhat waterproof boxes because we all got rain during the experiment. But we did get lucky. So on the left, that's one of the lightning strikes recorded by one of the cameras. On the right, so the one on the left is quite short, so I'm actually repeating it in this video. The one on the right isn't repeated. It's just that we had a crazy amount of strikes hit the same point. Unfortunately, only 1 camera caught the one on the right, but 2 cameras did catch the lightning strike on the left. So that's enough to do ranging and thus 3D reconstruction. An extra word on how we get the 3D map. The US has a lovely government institution called the Geological Survey that provides really high precision down to the meter airborne LiDAR data, so we can download free excellent elevation maps. The European Space Agency has something similar for images from space, so you can also download a very high quality image of the ground. If you combine the 2 with a bunch of open source software, you get your lovely map. Now, the mistake I mentioned 2 slides ago is the fact that latitude and longitude don't map to dimensions across the globe. It's only true on the equator. On the equator, half a degree of latitude is then half a degree of longitude, but as you go north, your longitude is worth less and less. As a result, the map I used to sort of align the fireworks camera is actually distorted by a factor of 20%, which is probably why I had such a hard time aligning it. So this is what the alignment looks like. Fiddle with a rendered image of the events change the transparency to try and align it with the background. And we can then project the 3D plot of the lightning, and we get a lovely video of that reconstructed 3D strike. Of course, the next step is to automate the process of realignment so that we can have not just the whole lightning strike at every point in time and have a 4D reconstruction of sorts of the lightning in 3D space unfolding over time. And that's it.
Right, so here we were trying to determine if we can use the event camera to track the motion of sand for the purposes of understanding the dynamics between wheels and terrain for designing better and safer wheels. So here on your left, you'll see our highly scientific apparatus where we engage in a rapid rotational deceleration due to unplanned contact with unconsolidated material. They'll be very generously lent his bike. And so what we're going to do on the right is the event camera video of the wheel that's about to come in here on the right, contacting the sand. You can see the particulates fly, but then you can also see at the very end there, you can see the sand as the wheel breaks flowing in response to the settling on the ground. Right there. So this is very good news. I think this means that we can actually use this. We have some more data that we've collected, including some embedding from Matthias's robot. And the notion is to process this data and then try and sell this concept to people who work in wheel design for planetary robots. So also this is the Mars rover project. We have a plan, still have a plan. Oh, sorry, we have a plan here. We still have this plan. Basically, we have 3 levels: high level planning, goal selection, trajectory planning using dynamic neural fields, and then adaptive control doing using Ningo style approaches. This is the plan. This is the simultaneous planning and acting in the DNF format. So it turns out that extracting the connectivity matrices was a little bit more challenging than we anticipated. So this is going to be post-workshop work to integrate the system completely. And of course, Catherine built this very nice controller that we did. Thank you. And then we did actually manage to interface it with the Copelia sim and drive a robot. And then some of this work will lead into some a presentation that's about to come up next. So thanks.
Okay, so I mostly work on visual attention, so I try to understand how to join this for space applications. So these are my Avengers, as you can see, and what we have done here is, so this is work from the previous week. So we are trying to use some sort of score for the saliency map. So each event has a score that depends on the scales and different scales in space and time of events that happen. So this work has been done mostly by Akwasi and us, and it will go ahead. We already have an overleaf, so we are very happy about it. So let's start talking about this. Come here. So this started at Toby's place. So we were there and he goes, so I have a robot. And I was like, fine, I have attention. So let's try to merge the 2 things. So basically what we have is that we get the frame from the camera, which is a time of flight camera. And then we have also the depth, right? So, sorry? Yes. No, sorry. Okay, yes, it's a laser. Okay, so we have again the frame, and then we have here the depth, and then what we want to do is that we want to feed the proto-object model with something, and with something for us is the multiplication of the 2, because we want to enhance also things that are very far away. So we feed basically the model with this image, and then this is the proto-object model. I talked about it in my talk, and let's say it tries to detect objects, and then at the end we have a saliency map. Okay, so then at the end of the saliency map, we have a maximum point of salience. So when we have this point, we extract the average depth. We extract the average depth here, and then we tell the robot somehow how to go if forward or backward, right? So we have some safety measures here. So if it's like close of 20 centimeters, we then tell the robot to go backwards, which actually is the only thing that works nicely. But here we have the monitor that is giving you the information of the saliency map that we reproduced there. And the last thing is that we are trying to do the pipeline fully spiking based. So we are working with Michael for the Ningo, for the control. And we're also starting to work with the scenes instance back. So we let you know when we will land on Mars with the neuromorphic robot. And you want to add something? You want?
No, that was great.
Yeah, the other Avengers, thank you, yeah. It's not bold. Okay, so I came here with the dream, guys. I wanted to use this segregation of object and background motion that we have in the retina. So these are object motion sensitive cells, and as you can see here, these are different experiments where you have the eyes moving, and also objects in the scene, and then you can see that basically the response of these cells are completely suppressed if only the eyes are moving, right? So this could be cool for ego motion suppression and could apply, right, when we have stars and satellites that are going with different speed and different motion and different direction of motion. So there is this nice model that is basically telling us that you have some bipolar cells, that they're you have the center and the surround that is kind of repeated all over the retina. So you have the bipolar cells that are part of the surround, and bipolar cells that are part of the center, and then you have the bipolar of the surround that are connected with some amacrine cells. And so if the surround part of this basically different of Gaussian, if the surround part is very active, then the amacrine cell is gonna completely inhibit this ganglion cell. So this is kind of the how it's working. So let's go directly to them.
Yeah.
Please.
So Sebastian and me, we were trying to train spiking neural networks to compensate for ego motion. And for this, we constructed this artificial data set in which we have like this Korean ego motion background and like random objects moving in it. And we try to extract those objects, as you can see here in the targets. And for this, we started off with like non-spiking trained filters. And so we trained a Mexican head filter, which worked quite well. And we also trained a random filter, with randomly initialized weights, which kind of turns out to have like a similar structure, of course. And then we went on to spiking neurons, which you can see here. Same scenario. We have like the memory potential of the leaky-integrated fire neurons, which we implemented in NOS, and their corresponding spikes here, which corresponds to the extracted objects. And we train the filter based on the conversion distance here, which you can see here. And we also tried random filters again. And this was only the first step, because actually we wanted to train filters in like more realistic settings where we have like this data set that Sebastian extracted.
Yeah, so obviously it'd be ideal for us we've done all this so far, but it'd be ideal for us to perhaps fine train and test the spiking neural network on some real data. So we took about 10 gigabytes worth of DBS event stream data. Where's my list? Down here. If you can see in this video down here on the bottom right-hand corner, we've got some motion of interest clips. So I basically got Leo and Joshua to throw a football in front of the DBS camera, and I changed the settings so there's absolutely no noise or whatever. And then I overlaid this with some ego motion here, just like all sorts of different, like moving the camera around, and we've got 10 gigabytes of that, but we just haven't quite got time to use it to fine train the model. So perhaps after the workshops are finished, we'll take the opportunity to see whether that works well.
Yeah, and do you want to add anything?
No, it's fine.
And here I just want to highlight that we also are working with team, and we are trying to do the same kind of filter on Spinnaker too. Let's go ahead, Paul.
Yeah, so in a similar vein, you can use just simple spike independent plasticity to learn simple features to do ego motion and or saliency mapping. So this is what we're trying to show here with the gold and purple ones. The purple one you can't really see because of the contrast, but the purple at the top is showing the exact same representation. But this is on the astrocyte data that you'll see a lot more of with the satellite characterization groups that are just coming up. But this is just an easy way of separating how to get the ego motion of the stars and or the satellites separate from each other so they can start to do more complex characterization.
Okay, Leo.
Hey everyone.
Yeah.
Yeah, sorry I couldn't be there in person. Okay.
Face.
Oh, I'm calling on my phone.
It's okay.
Yeah, I'll turn it on.
Thank you. You're gentle.
Am I good?
Yes.
Yeah.
All right, so I know I'm short on time, so I guess our job here is to basically design like the simplest thing that can detect and then filter out ego motion from like jittering or shaking the camera. So on the top left, you'll see like a detector, and it detects motion that only goes from like pixel A to pixel B. It has a time constant, tau A, and you want to set that to be slower than basically any of the ego motion, but faster than any of the real moving objects, so you don't accidentally filter what you don't want to filter. On the top right, you need 4 of these to cover kind of all 4 cardinal directions. So I have 4 per pixel. If you consider a cluster of these in like a receptive field, you can basically predict the motion of the events by just like tallying all the detector responses across that field. It actually works surprisingly well. Like you can get within like 10 degrees of like what the original motion that you're sending in. Then you can compare the motion in the center versus the surround. If they match, then it's global ego motion and you can filter it out. So like the bottom left. If the center is moving antagonistically, like the bottom right, then the angles don't match. So there's like an object moving there. So you don't filter it out. And that lets us decipher whether, there is a moving object or if it's something you want to filter. So you take these, you tile these overlapping receptive fields across the camera. And then whenever each receptive field detects this ego motion, it deletes events from the center. Otherwise, it does nothing. So this is all simulated stuff. It works pretty well. Next up, we're going to try this on like the real astrocyte data provided by the space team. So more to come. Thanks.
Thank you, Leo. Ricardo. Sorry, I feel.
Yes, I'm here. Can you hear me?
Okay, so Riccardo comes from the Politecnico di Torino, and they worked from remote, and it's so cool that we have some remote folks that that are about to present something. Please explain your model.
Yes, here the basic idea is to exploit the same idea behind the image segmentation provided by the unit. And here the target is to extract the kernel provided by the training of this kind of net to generate another spiking neural network able to extract only the pattern of the data that we want to isolate respect to the ground moving in the ego motion application. And so here in the right hand side, I think for you, there is the first representation, the first output provided by the CNN-based approach, like the unit directly. And in the bottom part, we have more or less the same image provided by the spiking convolutional neural network of the unit. So in the source, we have the moving object and the background, while in the left-hand side, right-hand side, sorry, we have only the target without the background provided by the ego motion. That's
Thank
all.
you.
Thanks.
Thank you so much. So this was these were all of the approaches that came out, and I'm very happy about it. So we have all of the code for each approach pushed, and we will go ahead, and I want to see where we converge to like a nice coherent solution, but I want them to explore their ideas. Thank you so much.
Yes. All right. Hello again, everyone. Thanks for your time. So we're the satellite characterization project with the important caveat of with spiky neural networks, with a laser, of course, with spiky neural networks, as somebody's got to do it at the Neuromorphic workshop, right? So a lot of people have contributed to this project in different ways, and we should say special thanks to Giulias for developing the classification pipeline, and Jules for the tracking pipeline, Tim for the work on maybe mapping this to Spinnaker, and we should obviously thank the in-house consultants of Jens and Michael, who have helped a lot. So basically, you've kind of seen this data set. These stars and these satellites look pretty similar. The main distinct characteristic is that the satellite will be moving in the opposite direction of the global motion in the background. This is happening because the telescope itself is panning across the sky. Oh, thank you. You okay?
Yeah, we need a point. No?
Yeah.
Go on.
Here it is. And so we needed more data than the data available. So we basically created a synthetic data set based on actually the ego motion data set that Elias created. And the point here is we wanted to distill the fundamental feature that most objects are moving with uniform motion. Those would be the stars, and one object is moving in a different direction, and that would be the satellite. We tried a lot of different things for what felt like a simple task, but I think the nuance here is that those satellite features are relatively sparse given the overall frame of the data. And moreover, you're learning a spatio-temporal distinction between something moving against other things moving, and these could be any directions. However, we leverage two things. One, the low-pass filtering properties of leaky integrating fire neurons, which can drag features, in time across space, making it basically a computer vision task with a bunch of different streaks across the screen. And because of the simplicity of these streaks across the screen, it was well suited to just use these Gaussian kernels suggested by Jens to pick up on these simple low-level features. And we get up to about we have a new number here, it's 87% test accuracy now. And we expect with some more tinkering and working with the architecture to improve that number. Oh, and here's the overall architecture. You're just feeding it through these filters and then to a layer of leaking integrating fire neurons.
Yeah, so one, to get some intuition of about what's going on in the network. So you can see here basically that some different like Gaussian distributed kernels and like the membrane response of leaking integrating fire neurons and their corresponding spikes. And what you can see, what they learned, what the effect of those kernels are is that basically it kind of enables the network to separate like motions in different directions. And this effectively, for instance, here you can see like one satellite moving in this direction, and here like there's some kernels in which you only see like the stars moving, and this effectively empowers the network to relate movements in different directions in order to determine whether there's an object or a satellite or not. Yeah, and yes.
Yeah, so my part now, my idea was to use a similar architecture, also spiky neural network, to track the satellite. So meaning that we would have the detection task that Elias was doing with his network. And in addition to this, we would have also the position of the satellite. So here you see we use the same generated data set. Here for the visualization, you just have an accumulation. And basically the task was to localize the last position of the satellite trajectory. So this is the ground truth here that you see. Yeah, so we can see here that at the end of our SNN, we take the maximum voltage value of our last layer, and this is the prediction to be compared with the ground truth here. So we can see that we are able to track quite efficiently the position of the satellite. Yeah. Another just quick, I just wanted to mention quickly another side project that we did mostly with Gregor, which was how to tell satellite apart. It turned out to be quite difficult for most satellites. So here you see the spectrograms of the event activity of different satellites. And it was very hard. We did the correlation analysis, PCA analysis of satellites. And one thing that turned out to work well was classifying with ANN spectrogram of tumbling and non-tumbling satellites. So here we achieved 93% accuracy, but for other kind of satellites, it was pretty hard to differentiate. Yeah. And
yeah, in conclusion, I think this was a nice exercise in spatiotemporal data with subtle features And we learned a lot of useful lessons, and importantly, we did it with spiking neural networks, which I think is a nice justification for maybe putting some of the cool hardware a lot of people work on here up into the sky, which would be amazing. And I think that's pretty much it. Thank you for your time.
We
It's been
should,
a-
we should add that we designed like the networks in a way such that we could like export it into spinning.
Exactly. So this is very simple data frames. By the way, I forgot to mention, thank you, Gregor, for all the help with processing data. We've kept these very simple examples with the expectation of putting these on hardware. And actually, we think maybe we try low EE and brain scales, and this becomes an inadvertent kind of benchmarking between different hardwares. Could be a lot of fun. Anyway, again, thanks everyone for the awesome workshop. It's been amazing.
Hello. So this is a similar work what the previous group has done, but the approach has been to do something in an asynchronous way and a very simplistic way where you don't use machine learning at all. So basically we have this recording, and if you can see, all these things are stars which are moving uniformly like in the same speed, in the same direction. And this particular thing is a satellite which is moving in a different direction with a different speed. And in this entire recording, you have noise as well as hot pixels. So basically, the differentiable factor over here is the speed and the direction of this velocity. So basically what you can do is, you have to somehow transform these events into the velocity space so that they get segregated over here. So essentially what happens is, as the events keep coming one by one, you have to cluster them based on the distances. So once you get the initial estimate of the centroids and the clusters that have been formed in the recording, with each incoming event, the clusters will move as in the direction of the motion. So now with time, you will get to know how the centroids of the clusters are moving. And because you also have the time information, you'll get to know with what velocity the clusters are moving. So once you plot the cluster's velocity across the X and the Y dimension, essentially you will start seeing that all the stars will start forming a sort of a cluster over here. The satellite will appear as an anomaly, and hot pixels essentially are those pixels which keep firing irrespective of if there is a change in the intensity or not. So essentially these pixels are not moving. So they will come to the 0,0 point and you can eliminate them. So basically it does not involve any sort of explicit filtering. The algorithm itself takes care of the filtering as well as the clustering, and you will be able to find out that. So over here, this is the original recording. So this particular thing is a satellite. So this recording has noise, hot pixels, stars, everything. And this is the filtered recording based on the algorithm. And down, what you will see over here is the x-axis is the velocity across the x, and y is the velocity across the y. And as the events keep coming and updates keep happening, you will see that the stars will start clustering somewhere, hot pixels will start clustering in the middle of the graph, and the satellite will appear somewhere else. So the green clusters are the stars. In the middle, you see a lot of clusters, which are the hot pixels. And the cluster 4 that you see down over there is the satellite. Or maybe I'll just repeat it again, just to make it clear. So this is the initial algorithm. So the green ones are the stars with each and every update, they are getting clustered. And in the middle, you have the hot pixels. And this cluster 4 is the satellite. So now with every update, if you try to filter out the events or the clusters which are there across the 0,0 velocity, and then again do the filtering, basically you will be able to eliminate them, and only the clusters which are the green, which are the satellites, will appear. And so yeah, this is the recording. So basically all the stars will get clustered over here, and the satellite will appear as an anomaly somewhere else over here. So this is a simple filtering process to do satellite versus star characterization.
All right,
The
so
satellite was moving just slower from the background stars.
No, it was going faster.
I know, but if it was, and it wasn't orthogonal in a different direction. Would you like it to work?
Yeah, it would still work because the absolute velocity will be different from the absolute velocity of this noise.
Unless it's not moving, then it'll be a hot pixel, right?
Yeah, if it is not moving, it would be a hot pixel. But as far as there is a difference in the absolute velocities of the two objects, you will be able to differentiate.
We have to start using.
All right, so I'm going to talk very quickly about the Lego satellite simulator that we promised you. We actually built the thing. This is actually a recording of a real satellite exploding in space. That's Sat. There it is blowing up. I don't know why it blew up, but that's the example of what we were trying to go for. That was the inspiration for this. We built something not quite as sophisticated. But interestingly enough, I think there's some really interesting things we can do with this, because really this idea of being able to track a problem where you have a whole bunch of, or let's say an unknown number of pieces breaking apart and flying away. You want to be able to detect them, track them, and even classify what they are. Lego is actually a great example of that, because the pieces have structure. We can actually have a catalog of pieces that we know, and the results are quite dramatic, actually, as you can see over here. Unfortunately, Lego is actually quite high quality. It doesn't flash apart as much as we'd like. So now new plans to go into Team and buy lower quality Lego instead. But I really want to build a data set of this, and it's a really good way just to test tracking algorithms, detection algorithms, classification algorithms that happen really fast. So we probably still have this set up for a little bit while if you want to bash some things together, but a whole lot of fun, and the kids really enjoyed it, and so did the adults. So with that, thank you so much.
Right. So one of the reasons I love coming here is because we're full of dreamers here, like trying to make the world a better place. And obviously, that also includes working with event cameras, where we're really hoping to not just make it a better place for us, but also for the future poor students who get a camera or event file and have to process it somehow. And both Alex and I and a lot of others have been working intensely to solve that independently, right? And Alex came up with this wonderful name for wanting to take events from one place to another. We ferry AER events from A to B, and therefore we came up with this new project called Ferry, where we're literally trying to just solve this problem by converging multiple efforts. And so the hope is to be able to solve some use cases. What I want to very quickly do now is to run through some cases where we think this could be useful. So for instance, we want to read and write to formats, and there are many, many formats out there, and they are very, very different and very annoying to work with. But what I like about this approach is that we have a very, very simple command line interface. If you have a file, you can just say, give me this input file and dump to this output file. So for anyone using this library, i.e. poor, time-deprived graduate students, you just write these 20 characters and you're done, right? And the idea is this works for across all these different formats. So CSV, that raw, CSV, that raw, whatever, event stream, and so on and so forth. Another example is you want to be able to take a event file and cut some seconds of it, maybe 2 or 5 seconds, whatever. And you can imagine you then chain some kind of filters, like where you cut things and you chunk them into frames, and then you output them at some point into a video file, which is not an MP4C, it's an MP4, but you get the point. Sorry, laser pointer. And finally, we can imagine working with custom filters, because obviously we're not going to build a tool that fits everything. And what I really love about this approach, and this is pioneered by Alex here, is that you actually build the core in something called Rust, which is a wonderful framework, programming language, but everything is wrapped in Python, so we can just build all of this stuff in Python. That's also what the command line interface is based on. So this is really where the bread and butter development gets done. All the fast part can be done down here, and we can work very quickly in Python. So one example we saw before was where you can filter something out, but essentially we can do the exact same thing in Python, right? So we can read the file, cut it, chunk it, and that also means we can then at some point use our own custom filters with Python code. And so this doesn't mean anything to you. The point is to make it very, very easy to use. And I know there are a lot of competing frameworks and formats out there, but we're hoping this will converge some of the efforts. And if there are other people who are interested in joining this effort, that would be amazing. So I think finally, we talked about future efforts.
Yes, absolutely. So I guess our goal is to be somewhat orthogonal to some of the viewers out there, so the MetaVision stuff, JR or DV and so on, and really focus on processing, typically from the command line. So any application where you either want to render your files or process them, and grow sort of a Python ecosystem. So we're very much targeting, I think, the research ecosystem. not like the big industrial systems or the very easy just click on the button record, somewhere in the middle, I would say. And integrate all sorts of different things, see how we can grow this ecosystem whilst keeping perhaps our core principle, which is easy to install. I think that's the one thing we absolutely agree on. It needs to be pip install and that's it. Thank you.
I know that Gregor's not here, but a few years back, we started something called Tonic at the workshop, which he has kind of maintained and really grown over the years. Is there some relation to any of this?
There is, and actually we've been talking to Gregor about this a lot, because especially when we work with very dense data sets, for instance, it becomes very annoying to process it. So really the hope is to use this accelerated Rust core and some of the stuff I've been doing in the A stream, where you can stream things to GPU and machine learning accelerators to do exactly this. So the idea is like to feed this into Tonic upstream.
Idea would be to potentially hide this inside Tonic as a submodule that will use for that stuff.
That's really cool. I would love to see that. Thanks.
Right. Another one? Yes. So this is the second time you see this slide. I will try not to tell the same stuff again. But this is one project we've been working on also between the NIC and the space group. And this was for the presentation that Ryan and others gave earlier with the satellite data. And so again, the focus was laser. Thank you. And the idea was really to focus on this part. So to have at the first step, really a file from an event camera, stream it onto Spinnaker into a spiking neural network, into an input population, run the spiking neural network, and stream out the outputs. And so it would be really nice to have something like the framework that Jens just presented for the data conversion here from the camera. I was using a eStream right now to create, to create some UDP packets and feed it into the network. And we had Ryan, Jules working on the algorithm design here. One cool thing that came out as a side product, which Jason integrated right now into as an Android, is the export of convolutional and other layer types into Near. So we are more flexible with the networks that we can use now. We had this flow basically from SNN torch via Near to Spinnaker 2, which is what I've been working on. We set this up for another application, actually for this keyword spotting thing. There were a couple of different applications running, but now we have this general flow to go from an SNN torch model to Spinnaker, stream in the data, run the SNN, and read out the results. Who else has been working on this? Andrea Pignata and Gianvito Borghese from the Politecnico di Torino. And if these guys are online, they might want to tell something also about the interaction between event camera and host. So Andrea, Gianvito, are you there? Okay, no.
Hi, team. I'm here. So Andrea, unfortunately, have to leave. So yes, we have also worked a little bit on interfacing the event camera with the interface we have on the host for the neuron population that then tunnel the spikes on Spinnaker. Unfortunately, we don't have the physical board, and we were not able to test this link. But probably when you will be at home, we can agree and we can collaborate for testing everything.
Yeah, so thanks for this. As you see here, there's still the host in there. This was the first step to really stream the file from the host Spinnaker. Eventually, we want to build this up step by step to remove the host and directly interface the event camera with Spinnaker, which would also be a nice feature for next year, where the NIC group, for example, focuses on perception. And on the last slide here, you can see some of the data, which these are data from the Ego Motion project from Giulia. And you can, sorry for this. You can see on the left, basically the a visualization of the stars and the satellite, and you can see how this translates to the orange spikes here at the right. So the x-axis is the time, and the y-axis is the neuron ID. So you can see how this image visualization maps to the input layer of neurons. And then we recorded some output spikes, which at the moment don't make sense because it's not a trained network. But the idea is really to get this then running for satellite classification, tracking on neuromorphic hardware. Thanks for your attention. That's it.
We are out of time, but I'll keep it for one more minute because I do think it's important to sometimes talk a little bit about the things that don't work as well. You might have heard me at the beginning talk about the F-16 flyover we tried to film. Well, the data is not very exciting. It looks like an insect. In fact, we had trouble telling it apart from the insects. Using tripods to track fast-moving things, not great. Alex really struggled to find anything, let alone the plane. So, you know, there were a lot of things that went wrong, and that was lessons that we learned to get to where we are now. Perhaps my personal failure in terms of this was the ill-fated solar transit. So there was a day where the Chinese space station was transiting the sun. So Noor and I went down to Montrose with Andrew to get a solar filter. We borrowed it from the astronomy club. We were nice enough to lend it to us. And we got up really early to try and watch the pass at 6:30. We went up the gondola with an entire telescope, only to discover that that wasn't the right place to look for it. It was actually at the school, so we went back down the gondola. We made it to the school just in time for some clouds to come by, but by miracle, the sky actually cleared up, the sun rose, and we were right there to do the observation. And then, which is actually kind of fitting today, we just decided to do an update. Which is the whole thing. So, you know, best efforts, but I didn't give up. So I like this because we tried again. And that's the whole spirit of this workshop. We tried again to look at the sign for transits. And this is our setup at the beginning of the day. You know, we needed a box so we could see the screen. It kind of fell apart after that. And this is where we landed up. You can see the solar filter held on by tape, the incredibly important cardboard so we could see what was going on, and the fan to keep the whole thing from overheating. The upshot is we got absolutely nothing. But it, you know, was an exciting way to sort of try and get some data, and really solar transits are really interesting. We can see the sunspots and the corona. So if anyone's interested in continuing this is something we'd love to see. So with that, thank you so much. You know, the SPI group was fantastic this year. Gregor can't be here, unfortunately, left this morning. But on behalf of all of us, thank you so much for all your participation and interest, and we really had a great time this year. So thank you.
Okay, this is for us. Enjoy, and that's it.
I went to home though.
What do you like about this workshop?
The people, always. They're so nice, so smart, so helpful. I'm learning so much from them. Hello, I'm Steve. I'm working on revolutionizing memory in language model. I'm a PhD student at the University of Groningen in the Netherlands. The brain in there.
And what do you like about the workshop?
The general atmosphere, the people, the fact that you can work on crazy stuff for 3 weeks with very smart people.
What are you working on?
Revolutionizing, what was it? I'm Matthias Kamper from founder of IIS, and I'm working at the intersection of hardware, machine learning and neuroscience, but at the same time trying to also develop some products that make sense.
We were in the corridor, and Dana is just rushing through the corridor, shouting, "God damn it!"
What do you like about the workshop?
Well, for us, the scenic views and all of the inspiration that I can harvest, both during the lectures, but even more so in the conversations with many kinds of specialists.
Hollywood in an apartment overlooking Sunset Boulevard. He had a '69 Mustang convertible, and he.
I am Paola. I'm an electronic engineer. I am a PhD in hardware design. We are trying to do low power hardware accelerator, the best one, and yeah, let's see how this workshop will go.
Was he mad?
I said, Dana, what's the problem?
Hi, I'm Alex. I work at the International Centre for Neuromorphic Systems in Sydney, and I really like even cameras in space.
Well, he says, NIH rejected my proposal for the 5th time.
The fact that there are a lot of people, different people from every country in the world, it's very nice to meet different people also from different areas, different subjects and so on. So
Just the incredible diversity of people and the passion, I think.
And what have you learned here?
Not to sleep.
I'm Ryan.
Where do you come from?
Here, Colorado. It's the best workshop I've ever been to easily.
And what are you going to do about it?
Wasn't there yet.
Can you pixelate it?
Okay.
Like more than I've probably learned in the past year. I just feel like talking to so many people with such a high level of expertise in so many different fields that are related but different from what I do is just extremely useful. I mean, you can't beat talking to an expert about something. Yeah.
This is a chip that spikes when you wave a stimulus in front of it. Can you guys hear it? It's in Swiss German.
Hi, I'm Jackie.
Where do you come from?
Cambridge in the UK.
I've learned quite a lot on LLMs actually. I wasn't terribly familiar with the topic.
Say hello for me, say hello.
I work in like connectomics originally, so I came in wanting to basically go away knowing how to build an LLM and knowing how to analyze LLMs.
I'm Michael Furlong, the University of Waterloo and the National Research Council of Canada.
Hello, I'm Paul Kirkman.
I have learned so much about a completely new topic that is something that I've always known would be useful for the future. Hi, I'm Mara from the University of Tübingen.
So what are you going to do about it, Dana? I'm going to go to my office, call them up, shout at them to get it out of my system.
I like a lot working with people where I've only read their names on papers in the last 2 years during my PhD. Finally, I can come and meet them and work together with them. That's really exciting.
I'm Matej, the University of Manchester.
Introduce yourself. Introduce yourself.
Ciao, sono Giorgia.
Giorgia, veloce. Oh gosh. Questi video lo tagli, spero. Sì, sì.
Ask any questions about finance or companies.
I'm a researcher currently at University of Strathclyde in Glasgow, but I'll soon be at Western Sydney University.
Hi, I'm Satyapreet Singh Yadav. I'm a PhD student in Indian Institute of Science, Bangalore, India. Basically, I'm highly interested in space-based applications, and that's why I really like when it have an intersection with the neuromorphic applications.
Hi, my name's Sebastian and I'm from Brighton.
Oh, those amplifiers there, where are those?
Oh, yeah, so.
No, the other one, the top.
This one here? Yeah. So this.
Because it's an exciting intersection of theoretical neuroscience and computing, and it is a novel form of computing that is different from the prior models we've had.
I like the fact that we can talk to lots of people in the field all at the same time and bring together some ideas that are really interesting and just learn about things as well that you don't know.
State-space models for EEG modeling and also modifying SSMs to be more brain-inspired.
Hello, I'm Joshua Russell from UMass Amherst.
It's reading your thoughts.
It's reading your thoughts.
Introduce yourself.
No, wait, I don't want to do this.
Introduce yourself.
No.
Introduce yourself. Come here, please.
Okay.
Introduce yourself.
Hello?
Just say your name.
Actually, I think it's a bit too bright here and I struggle with the altitude a lot, but I guess the greenery is nice.
My name is Jason. Oh, I like this workshop because there's great people here and it's a beautiful village.
Okay, and now.
Do you know where she's from? Can you tell?
Oh, England. Next
Mamma
Spain.
mia!
Spaghetti. Pizza. Italy.
Oh, I'm learning all about circuits and neuromorphic technologies. We're looking at state-space models this year.
I'm loving the neuroscience talks. Also the fact that there's lots of experts that you can just ask questions about during the day.
I think it's nice meeting everyone, getting to talk to all the interesting people about their research and getting help from them. I feel like being able to do a lot of stuff hands-on is the best way to learn stuff, and I've been doing a lot of hands-on stuff, so therefore I've learned a lot.
What do you like about the projects that you're doing here?
Giulia, she's a wonderful spirit and she made me make this video.
And then I'm gonna send it again. Because in this business, it's over when you say it's over.
Would you suggest coming here?
Absolutely. I would, yes. Oh, definitely, yeah.
Oh yeah, totally.
Yes, 100%.
100%, yeah.
Yeah, for sure, of course. Totally, yes. Do you suggest coming here? Yes. Yes, definitely.
Everyone.
Yes, 100%.
Yeah, definitely.
Now.
Oh, it's okay. We all will too. Thank you all so much. That brings this to a close. Please help tidy and clean up, pack everything up. And then we will see you at the banquet at 5:30 at the Elks Lodge.
And who are the bosses of the cleanup?
You and Mike and yeah, Mike and Paula, I guess the main one.
You know what to do, right?
No,
Okay,
no.
so we have these beans. Please follow the instructions of the staff organizers to put things in the beans. We are not gonna move the beans today, we're gonna move them tomorrow. We're gonna just leave them by the door, and tomorrow morning we're just gonna take them down to our place. Because I don't think we have time to go once and come back in time for the question. But please, also, please help clean up the school from trash, from whatever is around, because we really want to come back again here and really find a place and it's great.
Sound good?
Okay.